Very good. So, welcome to 3524, Thermal Fluid Design. So can people online confirm that you can see, can hear me?
Yes.
Perfect, thank you so much. So this is not an elective course, this is a required course. Having said that, I still hope that it will be fun for you and that you would really enjoy this course. It's not going to be that hard. And this is also kind of a new course. So I've been in this campus since 2003. So that's like 19 years or something. But this campus, sorry, this course has been here only for 3 years. And it was done by the department based on the faculty feedback on the capstone. You know, like the climax of your education should be the capstone 4-3, right? 4-3-4-3 that you take as the last course before you graduate, and you're supposed to put all the knowledge that you gain in order to design an actual product or solve an actual problem, right? And their feedback was over the year that the design project does not go well, and the students have problem with that because, and they identified the problem, and they said, okay, then now we have to make a small course at the 3000 level that prepare the students for the capstone, okay? So that's why this course will be a little bit different than the other courses, because it's designed just to be able to get you to the design experience. And I'm going to explain today what's the difference between this and regular courses, right? But we're going to have our class every Monday from 4 to 7, and then we'll take a break. We'll also take a break in the middle too, right? And then we will have a discussion that's supposed to start from 7:20 until 7:30 till 8:10. And so that discussion, we will be discussing like the homework that you're gonna do and the design assignment, okay? So 30% of this course, almost 1/3, is supposed to involve you in some kind of design projects. And again, I'm gonna explain how is that different from like regular homework problem. What's the big deal? If I can solve a homework problem, why cannot just go ahead and do my design project in capstone or any other? Okay, and we are broadcasting live on Zoom, right? But we are not gonna keep the recording for you. So the recording will be available only for people who get sick. Okay, so you could think, well, why do I have to be sick to see the recording? What if I just want to watch this lecture over and over again? What's bad about this? And it's actually really useful for a lot of people to just watch the lecture over, especially the part that you didn't get. Well, the department, again, figured or realized that, and I saw this firsthand also last semester. If the lecture is available for you, especially for people not here, but people at home, they will be, okay, I'm going to wait for the weekend, I'm going to watch. And then come the weekend, and then the kids get sick, or I need to do this for my house, or my project at work is really, I need to do something, I have to do something for it. And you end up postponing. So as long as the lecture is there, you will tend to tell yourself, okay, I'm going to watch it later, I promise, you know. And they accumulate, and then there are so much, and then the midterm would come, and you suddenly realize that, man, I have 10 hours to watch, and you're not going to watch them. And so in order to encourage the students, especially those at home, to actually watch it while we are doing it, they said, we are not going to recommend that we actually keep the recording. But of course, if you get sick, you just email me and tell me I got sick, I couldn't see it, send me the recording. I will at that moment. Yes. I can't hear you. Well, nice to hear that. I'll try to exercise. Thank you. So the point is, we are not going to record them just to get people at work or so people at home to really be fully engaged. But in case you get sick, the recording will be available for you. All right. We're going to have office hour in my office or online, whatever is comfortable for you. If you want to just Zoom with me, I'm here every day. You just pick a time and we will Zoom, or you can come to my office. There is also 2 teaching assistants for this course. I think Bebin is sitting here at the back. Bebin, can you raise your hand? So Bebin actually took that course when he was undergrad, and he was the best student in the course at that time. And now he is a graduate student working on his on his PhD with me. And Saqib is also going to be our teaching assistant. You probably have seen Saqib if you have taken 3403 computer methods. So he was the TA for computer methods before. And so he will be helping you with the kind of the design project part. The reason why he would be useful for us is that in order to do those design projects, it requires iteration. It requires, let me try this. Does it work? No. Let me try this. Does it work? No. Until you find the best design. Or if you actually like to optimize the design. Like it's working, but I wonder if I can make it even better. I wonder if the efficiency can even improve. What should I do? And those things takes a lot of calculation. And if you have them on computer, that goes like this. But if you have them on paper, you will be done with one iteration. You're like, I'm done. I don't wanna. So that's why when we employ a computer model or like a simple simulation for the system that we are trying to design, and it will gonna be thermofluid system, something involved heat, energy, fluid mechanics, then it's much easier to do them on the computer. So that's why we will do this using MATLAB. All right? I'm not hung on MATLAB. You can do that with Python, and either Python or MATLAB. Saqib will be very helpful for you to, my program is not working. How can I print this into PDF file? Those things. And Beben should be able to help you with the regular homework and quiz. Yes, question.
First of all, will MATLAB be available to us? Because I don't know if we got paid for it.
So the answer is 1, Python is for free. You can use Python. 2, MATLAB it should be available on all the computers upstairs. And 3rd, I think. That I don't really know. Beben, do you know whether anyone can download MATLAB? Any student can download MATLAB or not?
Yes. I think they can download it for free using their OKeys account.
Okay, so the answer is yes, you can download it for free using your ID.
And the second question is about periods. How many people
I'm sorry, how many what?
How many people repeat?
Repeats? What do you mean repeats? Well, I got to ask the question here, not you. So yeah, let's ask that question later on. All right, now, again, I'm not stuck on MATLAB. So we can do MATLAB or Python or any other language that you want. The whole point is just to reduce the amount of time that you use to calculate things over and over, right? But having a computer code is going to really be useful. And for those who don't know how to use MATLAB, I promise it's going to be easy because I'm not going to ask for hard stuff. Very easy thing. Second, I promise it will shine in your resume. Okay, so having an extra line in case you actually don't really know how to use MATLAB, just to say, I know MATLAB, that make your resume look nicer when you start looking for a job. So even if it's gonna be a little bit troubling for you, it's worth every single minute or hour that you're gonna spend trying to learn. And again, we will just like say, do simple things, okay? And at the beginning, I'm just gonna give you the code and just ask you to push run. And later, maybe I can ask you to modify one line. And 3rd, maybe I'll just ask you to put things together. Here are different things, just let's combine them. So we will gradually go through this, and it should be really that very easy to learn, but very rewarding for you eventually. Okay? So So as we said, the goal is to learn how to design, model, and optimize a thermofluid system. So that involves thermodynamics, heat transfer, and fluid mechanics. There are prerequisites for that course, specifically heat transfer. And so people who didn't have heat transfer, didn't pass it with a C, shouldn't be in this course, right? Now, the first difference between this course and other courses is the textbook. So any other course, you should have a textbook, and the lecture notes should come exactly from that textbook. Homework come from that textbook. We live and read and breathe, and everything is basically that textbook. So, but the people who came up with the design of this current course that we have over here, so that we should make the student start to behave as if they are professional engineer, where you are faced with a problem at work and there will be no textbook for you to refer to. There are books that you can refer to, okay? And so you go to those books and you find the information, just like when you go to the capstone next year. So in the capstone, when you start modeling or like designing a new filtration system for the Jenks aquarium, or you are trying to make a new lift for Spirit to carry their heavy equipment, they will not give you a textbook with that project, right? But they will tell you go through all the courses that you had. But so that sounds really scary, but it's not going to be that level, because we are not there yet. We are preparing you for capstone, but we are not at capstone yet. So what is then what we're going to do? I'm just going to tell you that we need 3 textbooks that you already had. Okay, no new textbooks. Those already are the thermo book that you had in Thermo 1, the heat transfer course that you had in your heat transfer course, and the fluid mechanics book that you had in fluid, right? And you don't have to have those particular version. I mean, it's nice if you have them still new and you didn't turn back your heat transfer book, because I'm going to use it. I'm going to use the chart from there, specifically the thermal book. I'm going to use a lot of chapters and material from. So if you have it, that's convenient. Okay, but don't feel overwhelmed. Don't feel like, wow, I have 3 textbooks. What in the hell? No, it's that's what you are expected to have in real life. Not one single book, but you get information from different sources. Depending, do I need to remember what is efficiency of a cycle? Or do I need to remember what was the effectiveness of a heat exchanger? Or do I need to know what is the specific speed of a pump? So you pick the fluid mechanics book, the heat transfer book, the thermal book, and when you get those equations, put them in a MATLAB file. Here is my model for that system. Okay. So those are the 3 textbooks that I'm going to use, but any other book in those 3 categories are fine as well. Okay. But those are the ones that I'm going to use. So here is our class schedule that I will try to stick to. And there is dates here that you should put in your calendar. Exam 1, exam 2, and the final exam. And you can see the exams are 45%. The quizzes and the homework are 25%. And the design projects are 30%. So that make the 100%. And my A is at 85. So if you are 85 or higher, you get an A. B 75, C 65, and the D is 55. So now the late policy, or if what happened if you miss one of the exams, especially that we may get sick, you may get sick, and you also may be working and you have to travel. A lot of students actually have to travel sometime. So if you may miss any one of those exams because of sickness or travel, you just need to tell me ahead of the game, and you don't have to prove anything to me. You don't have to tell me, well, here's my COVID doctor certificate. I don't care. You just tell me I'm going to miss that exam. And what will happen is we will just wait until your next exam. And we will see what you score in the next exam. And we will use the class average between those 2 exams to calculate your score for the exam that you miss. If you miss the second exam, we will use the final exam. If you miss the final exam, we will just wait until you come back from the hospital, because that's the only reason why you missed the final exam. And that actually happened. One guy once crashed his motorbike on the highway coming to the exam. So I give him incomplete in the course, and he came back 1 month later on crunches in my office upstairs. My office is in the 2nd floor. And I gave him an exam in my office, and that's when he got his. So you can miss any of the midterm, but the final, we will just give you a makeup exam after you recover. The homework and the quizzes. So we're gonna have quizzes every single week, and they're gonna be very easy. And actually 80% of the quiz is just, 80% is gonna be just for being here, okay? So you're gonna say you are being here by also saying which row and which, of how far you are from the wall in that quiz. So you're saying I'm home watching over Zoom, or I'm sitting in the 1st row, 2nd row, 3rd row, 4th, and I am the 3rd person from the wall. The reason why we are doing this is because the university administration wants us to have seating charts. Maybe they will use it later. Someone gets sick, they will tell people around him, you know, he got sick, we watch for symptoms or something. But that will be 80% of the quiz. And then, so that's a B, right? 80% is a B. Now to get your A, you have to do a very simple quiz, right? And so it will be on the material in the class, but very easy. And I'm gonna help you too. And the reason why is just, I want you to stay awake, because it's very hard to stay 3 hours, right? Straight, especially if you had a full day in the morning. So I'm trying to give you as much incentive as possible to keep you awake, all right? So one of the incentive is there's a quiz at the end. You need to stay awake for it, okay? So now, what if you miss a quiz, and what if you miss a homework? Because again, you will be sick, you could be out of town, for all those reasons. So the plan for medicating, and all those are written here in the attendance policy. So the plan to accommodate for sick people or people who miss things because of travel is, I'm just gonna drop the lowest 2 quizzes and 2 homeworks. Or rather than dropping it, I could ace your lowest scores in quizzes and homeworks. So I'll pick 2 homework and 2 quizzes that you are lowest on them, and I'm just take you all the way up to 10. So you even they don't exist 0, you were not there, you get 10 of them. Okay, so this way we are fair to people who missed, but we are also even fair for the people who were here. Everyone get a chance to, but the point is that the people that will get sick will not get punished because they got sick. Okay, so that's what we're gonna do with the missed exam, the missed homework and quizzes. Now the missed project, that is a lot. And also the project is really important. I really like you to do the projects, because that is the whole idea behind this course, is that you can, when you see any design project, you are ready for it. You don't panic, okay? And so that's why that's the only one that has late policy. And so it's 50% off for a week. So you miss the deadline, you have a whole week to do it, and you get 50% off. But really the best way to get away from all those things is that not wait until the last night before things are due and start working, because you may get sick, your children may get sick, someone may require your attention, or something at work may require your full attention in the last minute. So make it a habit. Don't wait until Sunday to do the homework. Let's do it Saturday. This way, Sunday we are ready to get sick in case, right? Very good. So we talked about attendance, the mask policy. Everyone is encouraged to wear a mask. However, you are not required to wear a mask. So in case someone doesn't wear a mask, don't shout at him. The university does not require people to wear a mask, but we strongly recommend that you wear a mask. Yes. Go ahead. Yeah, sure. Let's see that. Sorry. So will the due date for the design project and the homework be added to the schedule? So the deadline for all those things will be the 4:30 on the day on the next week. So if I assign things, it will be due 4:30 the week after. Everything is due in 1 week, yes. I actually didn't finalize this yet. We will, I'm sorry, what? Yes, I'm thinking that maybe we shouldn't do group projects. I think maybe it should be individual projects. Okay, yeah. But I'm gonna listen to you guys. If you guys think that maybe near the end when things become bigger, maybe I will take your opinion. I'm gonna discuss this later. But for now, we will start with individual projects. And when a lot of people complain and say, this is just too much, I don't have enough time on me, I need help, then we will think about it. And I will do what you guys want me to do. So there is 30% on this thing. And my thought is that those 30% should be divided in 6 projects, each one is then 5%. Sound like the math sound good. And also give you enough time to pace out between them. But there should be homework every week. Okay, so there should be homework every week, except when there's projects. Maybe it should be easy so that you don't get overwhelmed. And then maybe 6 projects. So you will see that when I assign them, you will be able to see the deadline, right? So hold on, you will see it. Okay, final thing before we leave the syllabus is academic dishonesty. So this is basically copying homework from other people. So one, I need to tell you that it's very, very useful to work with other people. It's very useful to sit across from each other on the table outside and discuss how you're going to do that homework. What equation? It's even good to, after you solve those problems and you come back and you tell your friend, like, what did you get for number 1? And you would say 60%. And you tell him, I got 90%. How is that possible? Show me your solution. And it's okay, he can show you your solution. And you, yeah, I did this, wait a minute. What is that equation? All that is healthy. The moment when it becomes unhealthy is when he leaves the homework with you so that you can copy the right answer. I mean, it's okay for him to tell you or she to tell you, you missed this part, man. You have to do that equation. But it's not okay to leave the homework with you so that you can learn from it. No, you cannot learn from his homework, right? So you cannot do this. And I am very, very fanatic about this. And I have to tell you that in many semesters, I would send 15 people to the academic integrity office, and we will have 15 meetings, and I will spend 15 hours filing those forms and sitting in the meeting. And in most cases, every student signed that yes, I did this, and it's staying in his record, because I only pick the cases which is like slam dunk. So I give the student a chance, any way of doubt, I say maybe he didn't do it. But the cases I pick, and unfortunately, every year, a lot of people get slam dunk copying from someone or from check.com. And the reason why it's so easy to pick them is that, for example, in this course, check.com, last year, check.com solved the problem wrongly. The guy who they assigned to solve this problem mixed the humidity ratio with the moisture content, something called, the rate of humidity phi with the moisture content psi. He thought that they are the same. And so anyone who know anything about basically the course content will never mix the two of them. Okay? And so the people who copied from him, of course, why do people copy? Does anyone want to confess? Did any one of you copy before and can say why he did it? Yes. I can't hear. No, it's probably, that's not always the case. It's usually because, I mean, if you are lazy, you don't even come to college. Lazy, just stay home. But people copy because, I mean, they really want the points. That's not a lazy person. People want the points. That's why they copy. People also what? So that they copy. No, confused. You ask the TA and your amazing professor who is willing to explain everything to you until he's bored to death. But no, they don't copy because they are confused. They copy because what? Exactly. Exactly. This is the honest answer. They just wait for the last minute, and this thing is due tomorrow, and I have to wake up at 7 because I have a job in the morning, and I'm gonna lose my, how much is each homework? 1%. And they are not gonna lose the 1%. The homework is not one problem, 3 problem. So each one of them is less than 1%, is 0.3%. And even if you did nothing, you get half of that. So they are losing half of the 0.3 of the 1%. And that is too important for them to the extent that they risk their career and they risk being labeled basically cheater, right? And I will never be able to write a recommendation letter for them in their life because, like, how could I recommend someone like this? So it's so stupid to copy when I understand the pressure, but also notes that, you know, people who carry weight, I'm going to finish with this. People who do exercise know that the first 7 things, 7 left, do nothing. It's the number 8 with like, and number 9, when you cannot help and your friends like, come on, man, and you are pushing. That is the one that really build the muscle. So same thing, if the homework was so easy that you know everything and you are just like doing this, you are wasting a lot of ink and paper. You kill a bunch of trees for no reason. Okay, it's the challenging work, the one that require you to really think hard and get a cup of coffee. That is the one that will grow your brain power a little bit more, right? So the next time when you are working on an oil rig in the middle of the Gulf and the pressure is increasing and everyone is screaming, this thing is going to explode, and they come for your help, you are very calm and you are doing the calculation in your head. Okay, we need to lower the pressure by 1/2 so that the flow rate can drop, and because you were under that pressure. So what I'm saying is that this last hour, when this thing is due, it's a golden opportunity for you to really hold on and don't look to check.com. Don't copy the solution from someone, but really work hard to get it done. And in case all hopes are gone and there is no way you can solve it because you just don't really study the material and you really have to come back to my office or to Bebin office hour so that you can explain the whole thing from scratch because you have no idea what's going on. You don't even know what is the TS diagram, what in the hell they are talking about. Then that's okay, just leave it and lose that 1% for the whole homework, even if you don't want to submit it. And I promise you, the emotional scar that you will carry in your heart for losing that 1%, that is way better lesson than the 1% that you're gonna get. Okay, because no one loses grade over 1%. I promise you, if you are 2% away from your A, I'm gonna give you your A. Okay, so you can screw up 2 homeworks and you will still get your A or B or C or D. Okay, so no copying, but discuss as much as possible with each other. I would even go one more step and would say on record, it's okay to look at check.com for learning. It's okay to look at solve a problem for learning, but there is difference between I'm looking here to learn what they did and now I'm going to solve it, or I have no idea what is this, but they must be right. So let me just do it. That's not acceptable. That's counterproductive. And I remember myself when I was a graduate student in Michigan, and we were like 3 friends, 1 Russian and 1 Japanese and myself. And the Russian guy, math was superior. I mean, he would stop the lecture in the middle and I'll tell the professor, this is wrong because this is this and this. And we were taking this one math course with each other. And the math was so hard, like you don't understand even what are those symbols mean, what is going on. And there was this one homework, and he was like a really good friend, and he was explaining to me and the Japanese guy, you know, how to solve the problem, and we just didn't get it. And eventually he gave up and he said, just copy it and I'll explain it later. And I'm so proud to tell you that I refused. I said, no, I'm not gonna copy something that I don't understand. So that is the attitude. You can look at chat.com to understand what's going on, then flip it and do it yourself. But if you are solving like this, 1 eye here, 1 eye here, 1 eye here, 1 eye here, that is not learning. And they will screw up one time, you will copy from them, and my job is to report this person copied from Shag, and here's my proof. And it happened every year. And what is really killing me, and that's why I wasted maybe 10 minutes of your life talking about this, is that you would think only the D and C students do that. Unfortunately, no. The A students do this. The students that you know, every time you ask a question in the class, he answers. He has the brain power, but because he started at midnight before the homework is due, he just don't have the time to solve it. So don't be that person and don't, give me heartache. Don't copy. Yes. Do is what? I'm sorry.
Already paid my course before I started this year, and my work schedule. So I'm doing work. I don't know how to affect my class schedule. So if I can manage to avoid working Friday night between 4:30, 7, 8, whatever, that'll be okay. But on Friday night, some jobs got work past that it requires me to work that hard. Will you be able to be flexible with that?
Let's discuss this outside because this is a special problem. Let's discuss this after class. All right. So, question about the syllabus so far. Yes, please.
About the textbook, would you say that the international edition of the heat transfer textbook is equally useful as the US edition?
I'll go even one more, and I would say any heat transfer book will be useful, not just the international version of the textbook. And again, the philosophy of this book is that we are just using general references for information. When it comes to the homeworks, I'm gonna assume no one has a textbook, and I'm gonna spell the problem. I'm not gonna tell you solve problem number 10 from chapter 3. No, I'm gonna write it for you, right? And hopefully the lecture note would be enough, but you are here to gain that experience of like, I need the heat transfer coefficients of a flow in a pipe. And you would go and look all over your library or the actual library or the internet to find that equation. That is the point. So, I mean, it doesn't have to be our textbook and tell me where the page where I can get the equation. Good. All right. So, we talked about the syllabus, a little bit introduction about myself. So I did my master mainly computational. Okay, so in my master I didn't do any experiments. This is actually a page from my paper when I did my master. So this is called acoustic tube, where basically there is like a car muffler. And you send noise from this side, you have echoic or anechoic termination over there, and people measure the transmission loss of the muffler, or how much he managed to reduce the noise by basically putting mics over here. And so my master was all about making a numerical model of this so that we can predict the noise transmission loss, or how much effective this thing is as function frequency on the computer, rather doing it in the lab. Okay, so it was like involved basically writing the model and solving it efficiently so that you can see how much how much is the performance basically. And then for my PhD, I went to Michigan to do in aerospace engineering. So that was mechanical engineering. And then I did it in basically studying fuel atomization in high-speed flow, like jet engine, jet afterburner. And so we were using a shock tube. We will generate shock waves, and we will hit the fuel droplets with those shock waves and see how they disintegrate and what size they come up with. And then after that, I did my postdoc, which is like after you finish your PhD, you spend like 2 years doing more studies. So that was in the Air Force Research Lab. That's their supersonic wind tunnel. And that's me with more hair and way younger. And you can see this is from my experiment, so that you would send supersonic flow and you will send the fuel jets. So that's really in the kind of scramjet engine, the internal part of the scramjet engine where the flow is moving supersonically. You're supposed to inject and combust the fuel in supersonic flow. And so all those optics in the table was because we were doing holography. We were doing 3D images of the spray inside the fuel. And then I was summer faculty in the Air Force for one summer doing a work on again in scramjet engine. And then I came here in 2003. And so I would like you to make something like this, a slide like this. This will be the first problem in your homework. So one slide in PowerPoint that will introduce yourself to me. It has to have like a clear picture of yourself, your email, okay? And you'd say whether you have associate degree, what you are interested in. So here I say what I do my research in. You would say what you are interested in, maybe your career job, what you would love to work on after you finish, okay? And maybe you can tell me the courses that you already had so far, okay? And some cool picture of what the things that you like to do for fun, okay? So that would be introduction of yourself to me, so I know more about you. So in this course, we will learn three things, basically, three topics we are studying. So thermal fluid system, from our point of view, includes thermodynamics. Cycle like this, all power plants, whether they are running with natural gas. This is like Jinx power plant in South Tulsa, okay? So whether they are running natural gas or whether they are using coal or whether they are using sun or nuclear reactor, whatever the source of the heat, that heat is used to generate steam, and that steam go to a turbine, then into a condenser, then a pump. And that steam basically cycle go on and on and on. And every time you are turning some of that heat into work. And the rest of the heat get rejected into the condenser, in the cooling water that go into the river or go into the cooling tower in the air. And that's what defines efficiency of a cycle. So we need to learn how to plot this cycle on TS diagram, how we can model it, how we can optimize it, how we can improve it. For example, why the Jinx power plant efficiency is 40%, but you go to the Owasso one over like 20 minutes from here or less, and it's 65%. So why this one is 65% efficiency, and the one down south is 40%? What make the efficiency improve, and how we can make sure that our system is very efficient? See, again, it doesn't matter with what is the source of the heating. I mean, it could be just bunch of mirror that focusing all the radiation in that central furnace where it's so hot that you can see it's white. It's white because it's that hot over there, right? And the second part is the other topic that's important is heat transfer, and that's in every radiator, every HVAC system. Anytime you want to move heat from one place to the other, it moves across a wall, a metal wall. Cold fluid on one side, hot fluid on the other side. Okay, and we need to figure out how does, if we have already a heat exchanger, how it will perform. What is the best performance ever? It's called the effectiveness of the heat exchanger. And if we are picking a new heat exchanger, how we can pick this one? Not yet. And so those could be as big as a big boiler, where a person would be this small in it, or like a small heat exchanger, like the heat sink in any laptop. And the third part that we need to learn also is the fluid mechanics part, specifically pumps and piping for practical projects. If you are sending water through a filter system, coming back, maybe it's a swimming pool, maybe it's an aquarium, maybe it's just water going to the ground source heat pump and coming back. How do we pick the right pump? And how we can size it correctly? So now, question in class. I actually think questions in class are very, very useful. Okay, and I would encourage you anytime you think of anything to ask me a question. Okay, because one, there is not any stupid questions. Okay, the chances are if you have a question you hear this because probably this thing is confusing, or I went quickly through that, and even if there was a stupid question, you will still do us a favor by asking that stupid question, because one, you give me a chance to catch my breath. Two, you make everyone feel good about themselves. because you'll think they will say it's only him. We only got it. So I welcome question anytime. The only thing that I don't welcome is interrupting me. So you wait until it's the time for question, and then I will tell you. You raise your hand, and then I will tell you, yes, you had a question, and then you can ask a question. Yes, go ahead. I'm sorry, I can't hear.
I know you're talking about here the whole discussion, but now I think I legit question. Because a lot of stuff is going during like the common policy and it's acceptable. And some of the stuff we were talking about here, especially with new people get out, maybe like maybe shapes like
I can't find the question. State the question. What is the question?
actually, how can we take what we learned here and put it on a cosmopolitan level where it is socially acceptable for like aesthetics, make money?
Yeah, well, let's discuss this when we have the first design project. That's a good point. Let's discuss other limitation that is not just the numbers, but other consideration, economic, environmental, societal. We'll talk about those. So question are welcome. You raise your hand. I will point you that I got you, but yes, you lower it down, and then when it's the time for asking question, then I will tell you. In case you are worried that you will forget your question, you can always write it down. We talked about working together, and hopefully I scared you to hell about copying from each other. Hopefully did this work, right? We talked about the textbook, and we talked about all those things, right? All right, so now the part about why this course is going to be a little bit different from other courses, and it may give you a little bit of a scare. It actually, last year, it gave a bunch of really good students. The final exam was so scary for them. I think 2 or 3 people didn't touch the final exam, including one of the students that was like really great. I know him very well, okay? And he didn't touch the final exam. And fortunately, he did really so good that even when he didn't touch the final exam, he still got a C. That's how good he was. So why would that student panic that much? And what is the big deal about this course? So companies want people to be prepared for real world problems. They don't like them to just be trained to solve homework problem. Okay. So what is the difference between homework problem and real life problem? I mean, they are the same things, same component, but different approach. So here, there's a reservoir pump going through a bunch of pipes going back to the elevation. You probably have seen a problem like this in fluid 1. In fluid 1, this problem would be please calculate, here is the diameter, here is the pipe material, here is the flow rate, and calculate for us the pressure drop across the pipe. Okay, so how do I calculate the pressure drop? Does anyone remember? Bernoulli equation, excellent. So we would basically say, let me choose this here. And you would say HF is FL over D, V square over 2G, and everything is given. Since he gave us the Q, you would say, oh, the Q is AV, and the A is pi over 4 D squared multiplied by V. He gave us the diameter, he gave us the flow rate. So this is given, this is given. I will be able to calculate the V, put it over here. I got my V, G is 9.81, L is given, D is given, F, where do I get the F? Does anyone remember? From what? What is the name of that graph? Moody chart. It has F on one side, it had the Reynolds on the other side. Rho VD over mu. And there's one curve, if the flow is laminar, there's a bunch of curves for different epsilon over D. What was epsilon? Roughness. And he said in the problem, this is concrete pipe, you got the roughness, you got the D, you got everything here, you come like this, you get the F, you put over here, you got the HF, And then maybe it's a little bit more difficult because he said, we'll calculate the pressure drop, not the head loss. This guy will be in what unit? This one will be in the lens, correct? So this one would be in meter, right? So if I want to turn this into pressure, into PSI or kilopascal, what do? I need another equation, right? What is that equation? So delta B is rho GH, right? So delta BF is rho GHF. So what is the whole problem? You need to remember the formula. You need to remember the formula, plug in the number, right? Maybe remember like few things. This comes from here. Maybe I need to remember the continuity equation. But that is a homework problem. So now what is a design problem? A design problem would be we don't know what diameter. We don't know what pipe. Okay? So we don't know the diameter. We don't know the material. All we know is that they want to deliver the water from this place to that height, and they want you to pick the pump for it. So there is choices here. What material? Should I make this out of gold? No, too expensive. Should I make this out of wood? No, it will not last, right? So you need to go and Google what do they make pipes of? And you would say, well, they do it with cast iron, they do it all time, they maybe other material. Well, what is right now is there PVC, okay, will it take that pressure? Let me try. PVC is cheap, cast iron is more expensive, but which one will take my pressure? You make a choice based on what is being used currently, right? And then there's one part that you just have to be realistic when it comes to the diameter. Should I make it that small because that's really cheap pipe? Well, maybe if you are sending water from your garage to the backyard, you can go this small. But if you are sending it across the city from one reservoir to the city tank, maybe it needs to be a little bit bigger. How big? Should I make it, as big as you again go to what is really practical, right? So there are things that would depend on what is the state of the art, what material are people using. Maybe you wish there is something that will never rust and so light and so powerful, but it does not exist. So you just pick the next available, right? So what I'm trying to say is that the difference between homework problem and design problem is there is a bunch of unknown that you have to assume based on experience, logical choices, just be good engineer, right? And so that's what happened in the final last year. I'm going to show you, of course, before the final, I'm going to post for you the final from last year so that you can see it and get trained to it. But basically the final was like in every single problem, there were 6 problems, and each one of them, I would say, for example, imagine a pipeline like this, I would say, pick a diameter that sounds good to you and find out the pressure drop from it. Okay, so I never said what is the diameter. And so when there is like 2 things that are known, that student basically panic. Like, I don't know what to do, which diameter I should use. So in every single problem, for example, a Rankine cycle, like the one that we showed over here, I would say, we'll pick a temperature of the boiler that you think it would be. Like, for example, here, assume a relevant temperature and calculate the efficiency for me. So how can I get that temperature? Well, I would just Google what is the typical temperature in a solar thermal power plant. So why I'm doing this? Because I want you to be ready for the capstone project where you have to put the number yourself. You have to pick the material yourself, right? And you should be able to defend those numbers. You should be able to say, well, based on my calculation, when I assumed a pipe diameter this much, the pressure calculated was not too much. So it's okay. I think that is a good diameter. But for example, if I make a diameter this big, yes, the pressure drop will be so small, but the velocity will be so tiny that probably this pipe will be filled with fouling film very quickly because everything will deposit in it because there is not that much flow rate into it. And besides, it will be really expensive. Okay. So that's basically the bottom line, that the problem is a little bit loose. Okay, so engineering design is a decision-making process. That's the point. You have to decide. Of course, the more experience you have, the job becomes so easy for you. So you go to I have one of my friends, he worked in HVAC for system for buses. And so it's very easy for him, you just tell him the bus size, he will immediately tell you, what machine, what HVAC unit you need, because he did those exercises so many times. We are not there yet because you are still junior, but we are hoping that you get to that level. Okay, so decision-making process that draw principle from engineering and other fields. And the constraint on the system is not always efficiency or numbers that you can calculate. Sometimes it's just like, this is too expensive and I just cannot make it. We'll just be happy with a cheaper option because it's affordable, right? For example, I know for sure that my car, if this car flip, I'm dead. But I'm not driving a Hummer because it just will be way expensive. So I am choosing I made a decision that if I drive safe enough, the chances of flipping my car would be too small, that it's safer to have that one. Okay, so economic, safety, environmental impact, for example. And so things that we will deal with in our design project will involve things like this: Rankine cycle, mechanical vapor compression. Those are cycles that use for HVAC, but it's also here in this example is used for desalination. Okay, so things along those lines that would be heat transfers, heat exchanger, how large the area, how cold will this guy will get. So if you manage to model this, you'll be able to model a radiator, for example, in a car, or like a radiator in a big earth moving equipment, and you'll be able to tell them how much cooling we can expect ideally from something like this. All right, it's 5:30, so let's take a 10 minutes break and we will start after that. Restart. 10 minutes break. Yes.
So, Steve is having
You're gonna miss the quiz because they're planning to have the quiz at the end. So, but if you get in Zoom with your iPhone, you'll be able to do it.
do the quiz on.
Right? I mean, you can stay online with us on Zoom.
Okay.
Right?
Okay, perfect. Thank you.
Right, it's 43, so I think we should start. So, chapter 1, this is from the Selma book that I had on the reference, in case you're wondering where this is coming from, right? So he will start with introduction, basically, properties and system, control volume, all those things, huh? What's the property, what's the state? And we'll talk about the units and problem solving methodology. Okay, so the boundary is what surrounding our system or control volume. There's something called system and there's something called control volume. And the boundary is what you separate those guys from the surrounding. We exchange stuff with the surrounding. We give them work or get heat from them. So things cross the boundary, right? In case of a control volume, mass flow rate even cross the boundary. So a system, no material leave. It's a closed box. It's a cylinder piston assembly. The fluid, the steam, whatever is inside the gas doesn't leave. But a control volume is when you have things coming in and things leaving out, like a jet engine. A jet engine is a control volume, where you have continuous flow of air inside and continuous flow of exhaust leaving, right? So here's an example of a closed system where the gas is basically contained over here. Energy is released from the combustion, and that energy transfer into work by pushing on the piston. So the heat transfer to work, and some of that get dissipated to the wall as heat rejection, right? But you see that he say no mass cross the boundary of a system. That's what a system is. A control volume is when things continuously come in and leave. Fuel and air come in and exhaust leave. So that become a control volume. Okay. Very good. So properties of the fluid or the working fluid or material is mass, volume, energy, pressure, temperature. Some of those guys are intrinsic. They are, no matter how small you divide the system, you still have the same temperature, right? But the mass is not. Like if you cut them into half, the mass divided into two halves. So on specifically for steam, we can define the state just knowing two properties, right? So everyone know what is a TS diagram is, right? In case you don't remember that from fluid, so from Thermo 1, the TS diagram of water is like this. This side is what we call what? Saturated vapor, right? And this side is saturated liquid, right? And so a liquid at room temperature, which is what, like 20 degrees C, and atmospheric pressure, which is how much? 1 bar? This is 1 bar. Will exist here in this place. So if you are existing in that region, you are not saturated liquid yet. You are not hot yet. You are not, how hot you need to get in order to boil. How hot does water need to get in order to boil? 100 degrees at 1 bar, right? So this point over here is 100 bar. Sorry, 100 degrees C. So at 20 degrees C, you are here. And at 100 degrees C, you will be here. And then if we keep heating you more, what will happen? You boil. You start moving in that dome. What happens when you move in that direction? What does change? Your X, your quality, right? So the quality here X is what? 0, and the quality here X is 1 along this liquid, the saturated vapor line. Once you are here, you are saturated vapor. And if we keep heating you, what happened to you? You go up along that line, and that's called superheated vapor. Very good. Right? Superheated vapor. So now you can define where you are on that chart only using only two properties. For example, if you know that the pressure is 1 bar and the temperature is 200 degrees C, that's good enough. You know that you are here. So if you are here at that point, you can get your entropy, you can find out your enthalpy, you can find your specific volume, you can find everything. So at any one of those locations, all you need is just two properties. I mean, it could be also like the entropy and the pressure. If you know your S, S1 and B1, you find yourself here. And that is good enough for you to get all the other property, H, internal energy, right? So how do we do this? We use, what do we use? What do we use to get those properties? If I give you S1 and the pressure B1, and I ask you for H1, because that's what we're going to do in homework number 1. And I'm asking for H. What do I do? Where do I go to get the answer? Huh? Steam tables, right? Steam table. When I was a student many years ago, we actually had the steam table, and we used to carry it with us every day to the school. You know, the steam table was always with us. Fortunately for you, you have steamtablesonline.com, right? And we will also use MATLAB. So MATLAB is a programming language, right? It's not a steam table, but people write codes for MATLAB that do different stuff. If you go to the MATLAB webpage or like server, you'll find out that there's tons of free program that's available for free download, okay? Including this guy. It's called Xteam for MATLAB, written by someone who wanted to be famous and do everyone a service, right? And so if you go to our webpage, the canvas, you will find that zip file. You download that zip file and you do what after that? You unzip it, right? How do you unzip and file? You double click on it and your computer should take care of it, right? And once you unzip this guy, you will find, he will open into a bunch of files, right? So you will open into this xteam.m and xteamus.m. So that's the metric units and that is the English unit. Okay, so that MATLAB file need MATLAB to run. So you need to have MATLAB on the machine. And once you have the MATLAB on the machine and you downloaded that Xteam either from here or from somewhere else, that code is ready to give you the properties just like you are using a steam table. Except that when I'm using the steam table, I know the pressure and the temperature, then I flip through the pages until I get my pressure, and then I go along the rows to find the right temperature, and that's it. Then I read the line. Over here, because it's in MATLAB, what do we need to do? We need to follow the formats, okay, that code require you to do. Okay, so what is the code? There's a call function, okay, that you will give it the property. So for example, if I know the pressure and the temperature, and I would like to get the enthalpy, what should I do? I should do this, H, P, and T. So I tell you the enthalpy as a function of pressure and temperature. Okay, so what we need to learn is the call for it. Okay, so for example, let's find, so this is maybe gonna be your like 5th design project or something. And you can see that I'm heavily calling this code all the time. So here H1 is Xteam. Why Xteam? Because I'm calling that function. Can you see it with too small ones? So it's say Xteam and then between quotation H underscore P and T. And then I'm giving him the value of P1 and T1 because P1 and T1 is defined earlier in the program. So say T1 is 400 degrees. Okay, and P1 is somewhere I defined. So when I end up calling this H1 equal that simply say whatever value you have in P1 and T1, go ahead and use them to calculate H as function of P and T and assign it to H1. Okay, so for example, we can do H1 and then equal over here. I mean, we can copy this line and put it here so that you can see. We didn't give him P1, so let's give P1 equal 1 bar. Okay, and then let's do this. We didn't give him T1. Okay, T1 equal 400 degree, and then let's give him this command. We didn't run xteam yet, so we have to come here and run this because you need to see it. And then you say, should I always use that pass for it? Sure, add it to the pass. Okay, so now when we give him that command, it should work. It did work, but because I have this quotation, this semicolon, he does not produce does not show you the result. Now he does. So that is the H. Okay, so the H is 3,000. Now what is the units? What is the unit for this H and what's the unit for the T? Is it degree C or Kelvin? What's the pressure? That's why you need to read this manual. So this manual is just like 4 pages or something, 5 pages. And he will basically tell you, what property they are using. Okay, so he's telling you it's in bar, the pressure is in bar, and the temperature is in degree C. And then he will tell you the H and the S and everything. All right, see, here's the unit. Here's the table of the unit. So if you want to get the specific volume from him, it's going to be meter cube per kilogram. If you want the CP or CV, it's going to be in kilojoule per kilogram. Right, and all this is he's basically trying to tell you what you should use in the call to get those properties. Okay, the formatting of the code. So the first homework is actually gonna be running a code that I already will give you. Look at this one. It will be like this. I'm telling you that use this problem using MATLAB hint here, and here is the code. So the hint is actually the answer. So you will just copy this.
Sorry, can you share the online, the code that you're?
I am sorry, yes, sorry, I was not.
Thank you.
Very, very sorry. You online were not looking at it. So I was saying that you will, for the first homework, I'm going to give you the code that you'd write, the MATLAB file that you write, and you can type it here and you would run, or even better, you make something called M file. What's an M file? That is permanent file now. You just created a program that you will store here, and you'd say file save as, and I'm gonna call this, say I'm gonna put it on my desktop, and I'm gonna call this my, say, homework 1, problem 1, or problem 4, homework 1, problem 4. So now this is always there for me, and I can make it bigger. I can add to it. I can use it later on. Okay, so you can see how he's calculating different things. He's calculating the quality from the pressure and the enthalpy. He's calculating the entropy from the pressure and the enthalpy, right? What if I want to calculate other stuff? I just refer to the manual, looking at all those code. This is the manual of xteam, and it's on our Canvas webpage. So for example, if I want to calculate things for saturated liquids or saturated vapor. Let's examine, I want to use this, calculate this H. What is that H called? H, did we call it HG or HF? Tell me you have seen TS diagram before in term 1. You did, right? Yes? Many years ago, I know, but you have seen it. So you should remember, was it called HG or HF? HG, good job, HG. So this is HG and this is HF. Right? HG and HF. And for those saturated property, you only need one. For those saturated states, you only need one property. I mean, you don't need the pressure and temperature. It's enough that you know the pressure, right? So for any pressure, whether it's say 1 bar or like 10 bar, you can just ask him to calculate this HG or calculating this HF. And the same thing for the entropy or specific volume. You get those saturated properties just by using the pressure or the temperature. So how does MATLAB does this? You will see here in the enthalpy, there's something called HV_B. You see that? So this is now HV is actually our HG. And HL is what thermodynamic table call it HF. So F is liquid and G is vapor, gas, right? So HV is vapor and HL is liquid, HG and HF. Okay, I know when you change the symbols on someone, it's like really horrible. And I had this, I remember when I was undergrad, I had this horrible experience where one course, my turbo machine course, was taught by 3 professors. The course was so big, and they had 3 professors, and each professor had his PhD from different country. The older guy had his PhD from England, and the middle guy had his PhD from Russia, and the third guy, he had his PhD from Germany. And they were all teaching us this course from their notes, and the properties, even the symbol property, will be different from the 3 professors. So I totally understand the agony that you are facing right now, why they are calling this HV and not HG, but being flexible is what you have to be when you are dealing with different references. And as a professional engineer, you should expect yourself to use different references. So you should be ready to be able to, accept that sometimes people call this eta, but other people will call it phi, and other people will call it k, and right? Like specific heat, for example, some people call it specific heat ratio. Some people call it gamma, and other people call it k. And your eye should be comfortable either, right? Whether it's k or gamma. All right. So that's what we're gonna use in our design project. Okay. Of course, if you are on the just doing a homework problem, you can just use steamtablesonline.com or any other source that is good for you. All right. Just don't panic too much if the results is a little bit slightly different. It's okay. Right. So run the calculator, actually run spreadsheet. And then you tell him that you'd like the pressure and temperature, you say 1 bar and say 20 degree C and calculate. And he will tell you the enthalpy is, say this much. Okay, if we want to boil it, you will get the HG. See this one is on the other side. So how do I tell if I am on this side or that side? Meaning I'm using, because we will do this too, especially on the, say, a turbine exit. You know how the turbine expands the steam? So on a TS diagram, this would be like this. Say this is state 1, and then it will expand in the turbine. If it expands isentropically, it will be, say, to this pressure, it will be here. And then if it expands in real life, it will be basically like this. And so So let's have this point 2. And so let's imagine that the homework problem or the quiz or whatever is saying find H2. Okay. And all you know is that, then the assumption is that this is isentropic turbine. So what does isentropic turbine mean when it comes to 1 and 2? It means that S1 is the same as S2. Right? That's what isentropic means. And so he's asking us for H2. And so I need two property to calculate the H. And so the first property, and he said, say the pressure here, B2 is given 0.07 bar or something. So given B2 is 0.07 bar, and given that S1 is equal S2, and so S1 will be given from doing stuff on the top. So now we have S2 and B2. So how do you know whether that state is inside the dome or outside? Whether it's wet or superheated? How do you do that? Say that again. I don't have H2 yet. So the whole goal is find H2. So the only thing that I know is S2 and B2. And to get the reason why I want to know whether I am inside or outside is to calculate H correctly. So how do I know if I'm inside the dome and I'm wet or I'm outside and I'm superheated? From this S2 and B2, that's the only thing that you know. How do you tell from S2 and B2? Using the table. Nick is saying using the table. How? How can I use the table to find if I'm wet or dry? What part of the table I should use? So the steam table is basically, there is like pages for different pressure. Let's say there is a page for B2 that say B2 is 0.07 bar. And then the rest of the page is degree C, right? Several line. This is the superheated steam table. And right, so you basically say, well, here is 40, here is 60, here is 80, and then you get all the other property. And the other steam table is for the wet region. And for the wet region, they will have what? B and T together because they cannot be separated. In the wet region, if you know the pressure, then you know the temperature, right? Why? Because you cannot be along this line. This is again the TS diagram. You cannot be at 0.07 bar if your temperature is not, say, 40 degrees C. They stuck on each other in the wet region. Outside, you can be different. You can be at different temperature. But inside, B and T is the same. And so for that B and T, and they call them not just any B and T, they call them what? B saturation and T saturation. And then you will have here HF and HG. And you have SF and SG. And you have UF and UG. Those are the two extreme, liquid vapor of each one of them. And if that table is like really nice to you, he will do what also? Not only he will do HF and HG, he will also do HFG. What is that? And SFG. What is HFG? Anyone? Yeah, it's HG minus HF. He's so nice, he don't want us to even do the minus ourselves. He will substitute them for yourself. Why? Because we're gonna use that number so frequently. So he's like, let me just give it to you. Okay, so knowing that those things exist, back to our question. How? Yes, you compare your S2 that is sitting over here, hopefully. I mean, you compare the value of S2 with you compare it with SG and SF. You will see if S2 is bigger than SG, then you are superheated. or S2 smaller than SG, then you are wet. Is S2 is even smaller than SF, or maybe you are actually here then. Maybe you are. So this region we call it what? So inside you are saturated, over and here you are superheated, and here you are, if you are to the left of the curve, you are cold. What's the name for this guy? This region? Huh? It's called sub-cooled liquid. Oops, this is too much. Sub-cooled liquid or compressed liquid, either or. Why do they call them that? Because at this pressure and temperature, you're supposed to be here. But if we take you from this T saturation that correspond to your pressure and put you here, we cooled you. You end up being in that place. So for example, 1 bar, if you are at 100 degrees C, you are saturated liquid. But if we put you at 40 degrees C, you are subcooled. You are not saturated, you are actually subcooled. So the things in that region is called subcooled. All right? And why do they call it compressed liquid then? For the same reason. If you are here at 1 bar and 100 degrees C, that make you at this point and you're saturated liquid. What if we increase your pressure? What if we put you at the same 100 degrees C? We put you at 10 bar. Where you will end? You will end up here. So that is compressed liquid. Liquid with pressure higher than T saturation, or liquid with temperature lower than T saturation. So either or, you end up going away into that subcooled liquid region. Okay. Now, the last thing I want to say about this region, subcooled region, is that when I'm plotting the pressure over here like this, you know, different pressure, and a bomb, for example, will take you from here to here, and a bomb will take you from here to here. This is exaggerated so much. Those lines on the subcooled region are actually so close to that line. So close that I cannot really plot them. They're just on top of each other. What that mean? It means that to go from, say, 1 bar to 10 bar, you don't travel that much. You are almost there. The pump does not really have to make the water get hot to boil it. Sorry, to pump it to 10 bar. Right? Take very little. And you know that pumped liquid coming from a pump at high pressure is not really that hot. Right? That also means very good simplification. Since all those lines are almost on the saturated curve, that means that if you want that edge over here, and to be accurate, you always need two property, say the pressure and the entropy, or the pressure and the temperature. But because those lines are so close to the curve, what do we do then? It's enough to know, it's approximation, but it's a very good approximation to do what? To think of this point as this point, the point next to it, because those lines are not that far away. Okay, so let me make this clearer for you. So what I'm saying is a point like this, and if I want to get the enthalpy over here, that happen to be, this point is at 40 degrees C and say 1 bar. This point have the same enthalpy, almost the same enthalpy as this point, the point that is sitting at the same temperature. So basically what I'm trying to say, that the enthalpy of subcooled liquid is almost function of temperature only. It's not important to know its pressure. And that's also why when you take energy conversion 4263 with me, hopefully in the spring, you will see that the pump work in many problems is neglected. When we calculate the cycle and it comes to that pump, we say pump work 0, forget about it. Why? Because those points, those lines are on top of each other, and that work for the pump, of course, if you tell someone who actually sell pumps, the pump's work is negligible, he will kill you. What do you mean? Like, why? Like, we make our life selling pumps. What do you mean? Like, you cannot run without a pump, and it requires 3 horsepower. And yeah, but in the cycle overall thing, like if you look at the budget of the USA and then you figure, well, what is the budget for lights in the street? It's nothing compared to, don't we need electricity for lights? Yes, we do. But how many billions of dollars does it take to turn the lights in the streets? It's the same thing. So the pump work, yes, it's important by itself. But when you put it in a big cycle, it's nothing. Why? Because those lines are on top of each other. Okay, and that's why you will see that in many time when it comes to calculating the enthalpy of subcooled liquids, you will see that he is doing this. See, H9, for example, is HLP at P9. He's like just using the saturated property. Okay, look at this one. H3 is H line, HL at T. HL is the saturated liquid. Does this mean this 0.3 is saturated liquid? Doesn't have to. But he thinks this is good approximation. Rather than going with pressure and temperature, is enough to go with the temperature. Okay. So remember this could sometime speed things up for you. Question, you had a question. Okay. So we need to memorize all this? No, but we just need to know where is the file, and every time we need to have a property, we just come here and tell ourselves, what do I need? Do I need the density? It's rho. Do I need to calculate the specific entropy? It's S. What do I know? Do I know pressure and temperature? So I'm going to use this. No, I don't know pressure and temperature. I actually know pressure and enthalpy, for example. Then I'm going to use this. And I'm going to give him the actual numbers.
I can do my on the S2 or S part, go back on the slide to make it fit. I always look at that. So
Not you only. A lot of people, you know, I had like really good students confessing after the course that we had no idea what is a TS diagram and we didn't know what is saturated liquid. And it's never wrong to ask about anything that you don't know. What's wrong is to basically just not solving the problem. You need anything that is you don't remember. Chances are half of the class don't remember. And you will do everyone a favor by just telling me, explain this better for me. I don't remember that part.
I don't know how to do it.
Which part?
With I know the same can you explain it?
So all I want you to know at this stage is that the boiling or condensation of liquid happen along a constant pressure line in the boiler. And this section, we call it subcooled section. This is called the wet section, and this is called the superheated section. And we will solve a lot of problem over this. Okay, but for now, it's enough to know that you need temperature and pressure, say, to define this point. Once you define this point, or once you know that point, you can use those two properties to get everything else, enthalpy, entropy. Okay, and we will solve problem over them today. And your homework will be to get the value here in MATLAB, for example, and and use it to calculate, say, the work of a turbine or something. We will see that, right? So TS diagram, two properties enough to define a state. Okay. All right, so now that process, whether we expand in a turbine, heat in a boiler, that's called the process. And some processes are called isentropic if they are like vertically downward on a TS diagram. Some processes are constant pressure, isobaric, right? So the process define the path on the figure, all right? Extensive property and intensive property. So extensive property depend on the mass, like the total energy. If I have all this, it will have one amount of energy, but I divide them into half, the joules get divided. Okay, but the intensive property are things that no matter how small you fracture the material, every part still have the same. Okay. Equilibrium is when the system stop transferring from one state to the other. Once like all the heat transfer happen inside the system, then he's in equilibrium. His pressure is not going to change anymore. His temperature is not going to change anymore. All right? And when the system is in equilibrium with the surrounding, then nothing happened between him and the surrounding. He's not going to get heated or cooled from the surrounding. He's not going to expand or get compressed by the surrounding. You reach it basically steady state. That's the equilibrium. The units, never mix and match units, right? A lot, you'll be surprised how many students lose their A because of units, because in order to get an A, you have to get your answers correctly, right? So usually it happens because you mix the units, especially like things like kilojoule and joule, don't mix. Right? So you stick with joule, meter and centimeter doesn't work, right? And this actually, I was, you know, when I was a student, I was really frustrated anytime I lose points because of the units. And I used to tell myself, I mean, the problems are already hard enough that it's actually, we shouldn't really lose points over anything else. I mean, if I know the solution, I should get the problem. So I'm not going to lose points over units, and I would basically go to extreme to make sure that my units are correct. So what do I do? Like when I'm given a problem to solve, we always start, and I'm going to tell you here in this course also, you always have to start with stating what is given. And that part, just writing this part, you get 30%. 30% of the grade is just by writing down what is given in the problem. And you will be surprised how many students don't get that 30% because they don't, including in the final exam, they don't write what is given. Okay, so why do we need to write that given? One, it gives you a chance to calm down. You know, like I really get always nervous when I start solving the problem. So just by writing what's given, it makes me calm down. Second, many times it happened to me when I was a student, I still remember clearly that I'll be stuck in the problem, don't know how to go forward. And then go read again the problem, only realize, here is the pressure that I couldn't know how to do it. You just don't read carefully and you miss key inputs. So by putting this section, you are forcing yourself to decipher the problem statement into P1 is, you know, you would say P1 is, and if he said it's 10 bar, I would say 10 to power 10 to power 5. What is going on? 10 to power 5 Pascal. So I wouldn't write anything that's kilopascal, for example. If you say B2 is 30 kilopascal, I would write 30 times 10 to power 3 Pascal. If you say the temperature is like 200 degrees C, I wouldn't write degree C. What should I write? Kelvin. So the temperature should be in Kelvin, the pressure should be in Pascal, if he gave me any length, you know, like in centimeter or something, I immediately divide. I mean, I don't have to divide, I don't have to multiply, but I just have to write it like this. So I remember. And there was this really funny incident that's still stuck in my memory when I was doing my exam 1 year. And he was giving us the pressure, you know, B1 is like 30 kilopascal and B2 is 20 kilopascal. And of course, I wouldn't write kilopascal. I would write 30 times 10 to the power 3 and 20. And while I was reading the problem and writing this, I knew that it was isentropic expansion. What's isentropic expansion? When you drop like this on the TS diagram. So if you have a gas and he's going through isentropic expansion, you go vertically down. Isentropic expansion means S1 equal S2, right? Isentropic, no change in the entropy. So, and he was giving us like say T1, 20 degrees C, and he was asking for T2, all right? And so I knew that I'm gonna use that ratio thing, you know, T over T is equal P over B to power gamma, right? Gamma minus 1 over gamma thing. You remember that part? In isentropic expansion of a gas, T over T is P over B to power gamma minus 1 over gamma. And I know that the pressure is gonna just be the ratio. So it doesn't really matter whether it's in kilopascal or Pascal, because they cancel, unit cancel. But when I was like writing what's given, you know, and I was doing this, I was telling myself, you know, it wouldn't matter, right? And then the other part of my brain said, shut up. We said we're gonna stick to SI, we'll stick to SI. And then in the solution, when it comes to the solution, I was like, T2 over T1 is B2 over B1, you know, to power gamma minus 1 over gamma. And I was like, are you crazy? You know that are you actually gonna write it down? And I said, yes, I'm gonna do this. Shut up. And so I'm doing this and like, I'm pulling my calculator and I still remember that conversation because it took a lot of my brain power at that time. And I was like, so are you really gonna multiply by 1,000 and then divide over 1,000? You completely lost your mind. And then I said, no, I'm not, but just, I'm gonna cancel over here. But we said we're gonna stick to SI, let's stick to SI. So I was religiously sticking to never write anything in my answer sheet except if it's SI. Okay, and that helped me very well through my career. And when I was finally like a professor and I went to the AIAA conference 1 year, the AIAA is American Institute for Aeronautics and Astronautics. I hear the guy from Lockheed Martin saying that the Mars rover, the first Mars rover crashed because the scientists from NASA and the engineer from Lockheed Martin used different units for the thrust. One person was using the pound force and the other person was using kilonewtons. And I was like, yes, now finally justified. See, I wouldn't have done this if I was working for them. So it really pays to stick to, sometimes it's not that clear. For example, BSI. So of course, to start with, you can use English unit. I'm not just saying let's use SI, but let's be consistent. So I can use pound force and I can use feet, right? And I can use slug. If I stay with those guys for force, length, and mass, I'm fine. What's not okay is pound mass. Don't use pound mass. What's not okay is PSI. Is PSI is okay? Pound per square inch is okay to use for pressure? Yes or no? Is that standard? No, it's not. Pound per square inch is not. What should I use then? I should use pound per square foot, right? No inch, no centimeter. Meter or foot, right? Pound force or Newton. So you stick to one family of units, but you stick to the standard units of them, and you will be okay. All the equation will work, right? But you don't mix and match, and you don't use millimeter. Even if the number is really silly, and say the length is like 5 millimeter, and you say, well, do you really have to multiply by 10 to minus 3 to make it meter? Yes. Okay, so back again to solving the problem. So when you write what's given and what is required, you get 30%. Okay, and this will be graded on a scale of 1 to 4. So 1, if you miss them, you still get 1. 4, if you do them correctly, you get 4. 3, if you miss one of them, and 2, if you miss a lot of them, I guess. Okay, and that is 30%. The reason also why you need to write what's required is because a lot of time people just read the problem so quickly and don't remember or don't notice everything that's required. I remember one of my, he was really good friend, very good student. And in the final exam, I usually give 3 problems, but that particular year I gave 4 problems and he didn't even flip the page to see there was one more problem. And it was, I mean, he lost a lot of points over it, but I just I cannot forget that. So reading what's given and what's required in every exam and everything is really important. Take your time and write them down. Then the solution. And the solution should start with the assumption, right? And stating the right assumption is half the solution. Because if, for example, if you say isentropic expansion, assumption is isentropic expansion. That already is, gonna really be helpful because you already know, so S2 is equal S1. I'm gonna get S1 and then I'm gonna use it at 2 so that I can get the probability over there. So the solution is to write the equations. And that will be worth 40% of grading any problem. Okay, and finally, the final answer that you're going to just put it over here, say the efficiency is 0.4 or the B2 is 40 kilopascal. Of course, the unit over here is the unit that the customer is asking. If the problem say calculate this in degree centigrade, you don't say, no, I'm going to calculate Kelvin because degree centigrade is not. No, you do the calculation in Kelvin. But then when it comes to the final answer, you just convert. The same thing when we do any project for any company. We do our thing in SI, but then if they want the thing in horsepower, we convert at the end to horsepower. Just divide over 734 and it will get converted. But you do your calculation in SI, you convert at the last end. So that final answer is worth 30% of the problem. So again, every one of those is graded in scale of 1 to 4. So when you get your homework back from Beben, he will tell you problem number 1, 4, 4, and 3. So you said what's given, what's required, you did the right equation, but the final answer was slightly wrong. That's why you got 3. If the final answer is not there, you will get 1. So you get, say, 4, 4, and 1. If the final answer is there, but it's totally wrong because you totally use the wrong equation, you probably will get like, say, 4, 2, and 2. Okay, so 4, 2, and 2, that means you have what's going on, what's given, what's required. You use the wrong equation, and that's why you end up with a horrible answer. For, say, 2 and 1, you have the wrong equation, and you didn't even manage to get the final answer out of it. Does this make sense? So when you look at this, it will end up showing that eventually, if you never really get the right answer, you get a B. And I think that's really fair. I mean, imagine if someone, for whatever reason, never get the right answer. You ask him about anything, what's your phone? He give you the phone number wrong. Where do you live? He give you the address wrong. I mean, we need to mark that person with something so that we can warn the outside world. Never to let this person work alone. That person needs someone to check his calculation. I mean, he knows the procedure, but we just need someone to check the number. So that's our B student, right? And if you don't even know the correct answer, you don't know anything, you should get 4, 1, and 1. And when you calculate this, you will get actually a D. So 4, 1, and 1, what that mean? You are pretty good at English. You understand when someone talks to you, you understand what they want from you, right? But you don't know how to do it. That's why you get 4, 1, and 1. So you get a D, and you should, I don't know, work in as an assistant in the office or something. So So you realize that this grading is really fair, and you can even grade for yourself. It will be very clear to you that if I did equation wrong, I'm going to get 4, 3, and 3. Because one equation is wrong, and chances are the answer will be slightly wrong. Right? It's not going to be horribly wrong. All right? Questions? Okay. The design project will be a little bit different, right? Because it will involve more requirement than just calculation. Okay, so he's talking here about the different units that we should use. Okay, so pound, force is okay, foot is okay, right? Second is okay. In this English unit in SI, of course, kilogram, meter, second, Newton. Make sense? Pascal is the pressure, that's Newton per meter square. 1 bar is 100 kilopascal. And one atmosphere is how much? 1 atmosphere is, what's the atmospheric pressure? 1.01. Right, bar, 1.01325. So 1 atmosphere is a little bit bigger than 1 bar. 1 bar is 100,000 kilopascal, and 1 atmosphere is 1 bar. So we use this, we don't use this. We don't use PSI, we use pound force per foot square. Okay, absolute pressure and gauge pressure. I remember when I was junior taking my fluid course, or was it? Yeah. My only problem was, when do I use absolute pressure and where do I use gauge pressure? That was so confusing for me. So when do we use absolute pressure? When do we use gauge pressure? When it comes to the equation of state, B equal rho RT, this should be absolute or gauge. Anyone? The pressure should be an absolute value or gauge. What is absolute or gauge? For example, if I have a tank like this, and this tank have a pressure gauge, and that pressure gauge is saying 40 psi, that is 40 psi above the background pressure on that gauge. He's measuring the pressure, the gauge pressure. So if this is 1, this would be B1 gauge. How much on top? When you measure the pressure in your tire, it's 40 or 35 above what is the atmospheric pressure. So I mean, if there is absolute 0 over here, and this is P1, and this is B atmosphere, then this would be B1 gauge. Above B atmosphere. So when this guy said that the pressure is 40 psi, and then you are using that pressure to calculate the temperature inside the tank using the equation of state, should I use the 40 psi gauge or should I add 1 atmosphere to it? Gauge or absolute? Absolute, yes. This has to be absolute. Why? Because the equation of state really care about what is the pressure inside this tank. It doesn't care what is the pressure outside or how high we are outside. I don't care we are in the bottom of the ocean or in Mars. If you have that pressure inside, the equation of state should tell you the temperature outside, in the temperature of the fluid or the gas, right? So when it comes to the equation of state, when it comes to the TS diagram, when we are trying to say a turbine expanding or like a pump working from this to this, that is the absolute pressure. When do I use the gauge pressure? For example, when I have, say, a jet engine sitting, say, under a wing over here, and the flow is coming like this and leaving over here, this is Vn, this is V out, and someone is asking you to calculate the thrust of that engine. And what is that? And you are trying to calculate the thrust equation, and you're saying that the thrust is m dot V out minus V in. Huh? But then you need to also add the force is not only the thrust, there is also pressure force acting on the control volume. This is my control volume. That engine is called the control volume. Things are coming, things are leaving. That's called the control volume, not a system. There's crossing to the boundary. And the force that's acting on him is not just the thrust, but it's also B1. I mean, let's call it B1 first. Then later I'm going to tell you we're going to use B1 gauge. So B1 area 1 and B2 area 2. Is that the only forces that is acting, or you see other forces that is there? Any other forces there too that I'm not showing on my sketch? What about this? Isn't there forces there too? What are those forces acting on the engine's wall? Pressure force, right? But this is probably the atmosphere. There's probably the atmosphere everywhere, actually including here too. So they basically would say, let's, you know what, let's not worry about the atmosphere everywhere. Let's go above the atmosphere. Let's cancel the atmosphere from everywhere. Okay, and so if we do this, then let's just use B1 gauge and B2 gauge. So in our sketch, we will just plot things that are what's happening to my pen? We'll just measure plotting that are above the atmosphere. So we subtracted the atmosphere from everywhere. And here is V1 and here is V2. Okay. And here is the force that coming from the wing, holding the engine. Okay. And so now I define this positive direction and I write the momentum equation. I write the momentum equation for this, and I would say B1 gauge area 1 minus B2 gauge area 2 plus the thrust equal to m dot V out minus V in. Okay, and that's how I can calculate the thrust. So we use gauge pressure when we are trying to cancel the atmosphere from everywhere. So then we use the pressure on top of the atmosphere. Okay. Also, like in manometer problem too. Imagine if say you have like a pipe like this, and then you are measuring the pressure with a manometer over here, and it's like that. So when you calculate that pressure difference, say this is height is h, and you'd say B1, you can say B1 gauge is rho gh, because you are measuring it with respect to the atmosphere. One side is open to the atmosphere, and you are measuring it with respect to the atmosphere. Good. So absolute pressure when it comes to thermodynamics, gauge pressure when it comes to forces. Then we cancel the atmospheric pressure. So I'm explaining to here that gauge and vacuum. So the vacuum is opposite to the gauge pressure. So the gauge pressure is how much you have on top of the atmosphere. The vacuum is what you have under the atmosphere. So when someone saying the pressure in this tank is 25 mercury, 25-inch mercury vacuum, that means that I am lower than the atmosphere by this much. Okay. When does the pressure get lower than the atmosphere? Condensers, for example, in power plant, because they want to condense at low temperature, that necessarily means you have to use vacuum. So why? Maybe we should cancel this so it can get bigger. We should cancel this. Should make it on top. Yep. Yes. So the regular power plant, the Rankine cycle, it operates on boiler that take you all the way up to here, turbine that take you down, so even down here, and then a condenser that take you to subcooled liquid, and then a pump that take you up, and it keep going like this. So for the turbine to go from say 1 to 0.2, that work turbine is H1 minus H2. So to get this guy as low as possible, they need to take that temperature. Again, this is an TS diagram. They want to take this as low as possible, say 40 degrees C. How low can it get? It get as low as the cooling liquid that is cooling the condenser tubes. Okay, so for the steam to condense at 40 degrees C, if you open the steam table, or we go to the, how do we do this in MATLAB? Let's try to find the pressure that correspond to 40 degrees C. That would be a good exercise for us. Now, but it will probably be very small compared to 1 atmosphere. Again, 1 atmosphere is almost 1 bar, 1.01. That pressure would be like say 0.07 bar or something. So that difference between 1 and minus 0.07, that is the vacuum. Okay. And if you want to turn this into mercury, how many inches of mercury or how many millimeters of mercury, how do you do that? Let's say that the vacuum is 1 minus 0.07 bar, 10 to the power 5, because I don't do by bar, I do by scale. You guys online still can hear me, correct? Yes?
Yes, we can.
Thank you. Just like the laptop need to be charged, so we just need to I don't have that many socket. So we will, what time is it right now? Yeah, why don't we take a 10 minutes break? 10 minutes break, and then we'll come after that. That's a really good picture, yeah. Thanks. It doesn't matter, just send me what you got. I can print anything. Very good picture. What's up? Stick it in the line. Yes. Hey. Yes, I can hear you from here. That's okay.
I still got live around it.
No, you can't. You can just come here.
Well,
Come on, man. You know what's up?
I didn't really know it the first day of class was today. I thought it was Wednesday. I'm going through a breakup from them already. I got too much food before the night.
I'm sorry. Yeah, I'm very sorry to hear that.
I'm not. You thought you do it to my house, but you would not be sorry.
Okay.
You felt comfortable.
All right. So how can I help you?
If I leave early today, we're not gonna have a quiz today.
I think we're gonna have a quiz, but again, you can use 2 quizzes without a problem.
I don't want to lose no quiz.
Okay, we're gonna have a quiz today.
Those rules too.
No, you are not gonna lose anything. I'm gonna make it up for you. Like at the end of the year, I will find out those 2 quizzes, and I'm gonna give them you. I'm gonna take them to 10 for you.
Yeah, because already you started tripping last week. I'm still doing stuff together.
So again, if you have to leave, just leave, and you can leave for 2 days in the whole semester, and you're not gonna lose point.
I read leave. So I can make it up.
Everyone can score up 2 quizzes and still get 10 out of 10 on them. Okay, so use them at your discretion. If you have to leave today, leave. If you rather wait until you are really sick or you're gonna be out of town, maybe you should save them for. But if you have to leave, then you have to leave.
I'm just mad. I gotta leave for a spicy food.
Don't worry about it. Okay? Yeah. Good luck. Bye. No, 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 no. No, no crossing. No cheating, guys.
Well,
Take care. Good luck. All right. Let's start again. So again, online, you guys can hear me, right?
Yes.
Very good. So we were saying before the break is that to make this ranking cycle that work like this, work really efficiently, they need to make the turbine have big difference between the high pressure of the boiler and the low pressure of the condenser. And so that guy, to keep really low pressure, it needs to cool at very low temperature, okay? And that is happening by cooling it with a very cold water from the river or from the cooling tower. Then he can set at 40 degrees C, and that corresponds to a very low pressure, less than 1 atmosphere, say 0.07 bar. The way to get that pressure is to go to the steam table and figure out what is the pressure desaturation corresponding to that temperature, 40 degrees C, how low my pressure is. And if it's less than the atmosphere, then you are making vacuum. So the condenser will be under vacuum, right? And they can calculate this vacuum by measuring P atmosphere minus B vacuum, okay, the absolute value of the vacuum. And that difference can be expressed in kilopascal, or it's standard to actually use mercury, inch of mercury or something, right? Or torch, they also use torch, which is a unit of pressure. So gauge pressure is above the atmosphere, vacuum is lower than the atmosphere, okay? And we said that a good idea is like we can get it from X steam if we don't want to use a steam table, just by telling him what we need B saturation that correspond to that temperature, right? That is the line that we should use. So over here, if we say what is the pressure that correspond to, what is the pressure that correspond to let me make this bigger. You guys can see on the screen, all right? In that temperature, I'm going to say 40 degrees C, right? And I have to take the semicolon so that you can actually print. If you put the semicolon, mean execute, but keep the variable in your memory. Don't print it to my screen, because this is part of a big thing that I'm just going to calculate stuff. And then at the end, I just need to know the efficiency. I don't like to print every single line for me. But if I want to see that line, I just do this. And look at that. So at 40 degrees C, what's P2.0738? Okay? X steam, B saturation at T. That's the call for if you want to the pressure that corresponds to a certain temperature. Right? If I want to get this from the steam table online, then we will go to saturation property. Do you see that tab, saturation property? And so he can give it to you as function of pressure and temperature, or temperature and X. And so we tell him we are interested in 40 degrees C. Calculate stuff. The function is available only for registered user. Oh, we have to pay money. Okay. So this one is for free. So maybe actually you'll find out that sometimes you have to do this. You have to be creative in getting property. For example, in the X team, not every combination of property is available for you. You think that what if I have the specific enthalpy and the density rho? Can you give me the temperature? I know it can't. You just have to cook different combination to get it right. So I guess here maybe I could just go with 0.07 bar and calculate for the temperature. What? 0.07 and the quality is 1. And then say calculate. So then he will tell me the temperature is 39. So that is the temperature that corresponds to 0.07 bar. then what should I do next? I really want to know what is B saturation corresponding to 40. What should I do? I mean, he wouldn't allow me to check with temperature and saturation probability. He only can allow me to get the pressure. And I'm really dying to find out what is the B saturation corresponding to 40 degrees C. I guess 0.07 and it turned out to be 39. I wonder what is the one that do 40. What should I do? Anyone? Yeah, maybe I should do some trial and error. Why don't I try 0.071? And it's 3.26. I'm in the right direction, right? And just keep changing this until I get exactly 40 or pay the money. And I bet it actually calculates, we just didn't know how to do it. No, it's not free. Actually, he said register. Register does not mean you have to pay. You have to register. They will get your email and then they spam you until you pay them. Anyway, so again, fortunately, we have the MATLAB file, right? So we don't really need this, but just good. So why this is okay, good. Temperature scale, of course, we don't use degree C in the equation of state, but when can we use degree C? What scenario it's okay to use degree C? What scenario? It's okay to use degree C, guys. Well, so again, when we are using B equal rho RT, this has to be in Kelvin. There is no choice. But when can I use degree C in my temperature calculation? When we are what? Yes, when it comes to the delta T, that is correct. So for example, in the heat transfer, if you remember heat transfer course, the Q was like for convection, for example, HA delta T, right? T liquid minus T ambient, right? So over here, it does not really matter. People shouldn't, I get that question so many times. Should we convert? Like when we say like T liquid minus T infinity, should we do this in degree Kelvin? And no, it doesn't matter whether Kelvin or CC, right? But crazy as I was when I was undergrad, I would never use the, I don't remember that story. I just remember the pressure story because it took a lot of my time, canceling the stuff. But I'm sure I was like, no, I'm going to use Kelvin. Let them just get subtract from each other. I don't want to get my paper spoiled by degree C. Very good. So of course, also, degree Fahrenheit, we use actually Rankine, right, in the equation of state. And the conversion between degree Fahrenheit and degree C is super easy too. It's what? Degree Fahrenheit is 5/9. Degree centigrade is 5/9 degree Fahrenheit minus 32. You subtract 32 and then you multiply by 5/9. Or you just Google, conversion, and you will get the difference between them. So we said about the grading, right? About what's given and what's required and what is and the solution. But I would like to say something else about problem solving skills. So a lot of time we convince ourselves that if I read the solution and I understand what the instructor said, then I got the problem. This is as if someone who read a book think that he can write a book. The fact that you can read the book, you understand the book, it's very clear what the book is trying to say, doesn't mean that you can write a book. So why I'm saying this, it's not good enough to solve the problem. You have to always come up with a solution yourself, okay? Because it's the solution methodology. It's the reason why you went it that way. That's what you carry to other problems. Because you will never be asked to solve this problem over and over again. But maybe in your senior design project, you will be asked to do something that involves energy conversion. And you would remember, I did this method in this homework problem because energy was conserved, it just changed form. And we said those joules equal to that joules. Then when you face a new problem that have the same physics, you will follow the same procedure. Okay, so it's never the solution, it's the solution procedure. Okay, good. Question so far? So the question for online people is, when you say required, when you're writing the problem and you're giving 30% on given and required, what is exactly what you mean by required? So to start with, given is straightforward, right? So by given, I just need to see symbols and numbers. I want you to say this. B1 and T1, and row 1. So one funny guy sometime, like last year, he was like in given, he pointed to the problem statement, say the problem statement was on top, and he say, given, here, the problem is given. This is what given. No, I want you to spell out for me the numbers and the variables. Okay, so the same thing for required. I want you just to say required is the efficiency and say the overall heat transfer coefficient. It just show me that. And maybe you want to say that the heat transfer coefficient is required in 1 millimeter square Kelvin, for example. So it just show me that you know what is required. I mean, if you don't remember the symbol, or I mean, you can always say the cycle efficiency. That's also acceptable. But I don't expect you to say cycle efficiency if the system is operated at half the pressure. I mean, maybe that's the problem statement. We said calculate the cycle efficiency if the pressure is half by 2. You don't have to do this. You just say cycle efficiency or eta. That's good enough. It's just a way for me and to realize that you remember that there are 2 things that's required in this problem. And those are the 2 things. Does this answer the question? It's what we are looking for. Exactly. That's what is required. Straight out of the problem. You are not inventing it. No. Yes.
Is there a way you can find like an example of a simple homework problem?
Yes, we're gonna do this. Definitely. Let's solve the first homework together too, as a gift for me to show my goodwill. Okay. We are not there yet, however. I wanna cover one more thing before we go there. All right. So chapter 2 in the thermodynamic book, he talked about the first law of thermodynamics. That's probably the most important thing really in this course. We'll solve everything, not everything, a lot of things just using the first law of thermodynamics. Okay, so the first law of thermodynamics is simply an energy balance. It's like a budget balance for your house. How much money is coming into our budget, how much money we spend, the difference between them, if it's plus, that's saving going to go to the bank. If the difference is negative, that's debt that go to the credit card. That's basically the first law of thermodynamics. Joules coming in, joules leaving, and the difference is, are we storing stuff or we are losing from our control volume? Okay, and it helped with heat transfer, refrigeration, power cycle. Okay, and so he introducing the form of energy that first law is counting or basically making balance of. The first one is kinetic energy. Okay, so the kinetic energy of my of my mouse, if I throw it on you, is half mv squared, right? Half the mass times v squared. But the kinetic energy flux going into a controlled volume is not just a sphere, it's a continuous flow. So if I have a jet engine or a pipe and things are coming here with m dot 1 and v1, then the energy flux is not half m v squared, it's half m1 dot v1 squared. Okay, so this would be kilogram per second, right? And this would be meter squared per second. But you can tell then that v squared by itself, the unit would be joule per kilogram. So then when you multiply it by the mass flow rate, which is kilogram per second, you get joule per second. So the kinetic energy flux is in what unit? Joule per second, which is what also we call, what do we call joule per second? What? Correct. Okay, so half mv squared, that is energy, that's joule. But half m dot v, and that's what we use at the entrance of a control volume or the exit, that is joule per second, not just joule. Good. Potential energy, mgz. Again, this is the potential energy of this guy hanging there. So with respect to that data, you have this height, that is potential. So when you drop, you lose that joules and you turn it into something else, like kinetic energy. That's why you accept that velocity. But for a control volume, it's going to be m dot gz. And internal energy, we give it the symbol U. And the specific internal energy, the unit mass, is small u, and that is joule per kilogram. And for gases, that small u is CVT. And for steam, we don't use CVT. We go to the steam table, and we get what is the internal energy knowing any two other properties, T and pressure, entropy and temperature. Okay. And so the energy flux going into the control volume would be three things. Would be internal energy, potential energy, and kinetic energy. And the stuff that will leave would be the same. So if I have a pipe, maybe a pump over here that is taking the stuff from, say, the river and sending it to a higher level over here, this is 1 and this is 2. And we are trying to calculate the first law of thermodynamics so that we can figure out how much power does this pump consume. To do this, I need to do an energy balance in that control volume. I want to know what's the energy in, what's the energy out. So the stuff that's coming here is m dot 1 multiplied by, and I'm gonna write it wrong first, and then we're gonna, not really wrong, but it will change in a minute. So I'm gonna say U1 plus V1 squared over 2 plus GZ1. Okay, and of course, Z1 require you to define what is Z equals 0. I mean, zero could be here, or could be there. You just have to define what is the datum. But the point is, this is in joule per kilogram. This is in joule. Ouch, ouch, ouch. This is in joule per kilogram, and this is in joule per kilogram, and this is joule in kilogram. This is actually a good trick to remember. You know, whenever you're writing a formula and things are added to each other, they should have the same units. So if you are driving an equation and you are flipping from one page to the other and then you forgot the G, it's very easy. Just before you plug in the number, you check. I used to do that all the time. So I will drive all my final formula, and before I put my number, I check, does it really make units the same? Okay, and so that's why I remember till now that meter square per second square is also joule per kilogram, because it's showing the first law of thermodynamics like this, right? Very good. So those are internal energy, specific internal energy, right? Kinetic energy per unit mass, potential energy per unit mass, and they are multiplied by the flux. The same will be over here. And if there is difference between them, if the energy out is more than the energy in, it must be because of the power that the pump is doing, right? And that is the point behind the first law of thermodynamics. That's why it's useful. If it's a system, not control volume, there will be no m dot, just like joule, 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 not joule per second, joule per second, joule per second. So now that system, or the control volume, because it's open, can transfer work and heat to the ambience, to the surrounding. He can get heat from the surrounding, he can give work or take work from them, like a pump, electric power is coming in, right? And so he's showing that some of the work could be like compression, could be a fan, could be just electric wiring going into the control volume. That bring power in, mechanical, electrical power. And the sign convention of the first law is that when the control volume is actually doing work, like a turbine, the turbine do work on the ambient, on the surrounding, right? It has a shaft, and that shaft do work on the surrounding, which is the generator sitting outside or the load. Then that work is a plus. So the system is useful when the work is plus. When the work is done by the system. The opposite for the heat. Okay, so the heat again can happen between the control volume or the system and the surrounding. We could heat the surrounding, or the surrounding can heat us. When the flow is coming to us from the surrounding, when we are being heated, that is a plus Q. The heat is positive when it's done to the system. So that is weird, right? You think? Because like they are not, you'd understand if everything going out is plus and everything coming in is negative, or the opposite. But no, they rather have it like this. If you have a control volume, then when you do heat on it, that is positive. And when heat does work on you, that is positive. Okay? And as a result, the first law of thermodynamics say Q dot minus W dot equal to. So Q dot minus W dot, that is the net energy. Q dot minus W dot is the net energy delivered to your bank account, right? Q dot minus W dot is the net energy delivered to you. And so that is the reason why your output, say the output is here, this is 2, and this is 1, the input. That's why you will have more stuff leaving than coming in, right? U plus V, U2 plus V2 square over 2 plus GZ2 minus U1 plus V1 square over 2 plus GZ1. So the first law basically saying that if you have a net addition to you, that's why the output will be more than the input. Or simply, if the output is way bigger than the input, it must be because you are being given heat, or someone is doing work on you. That's why the stuff is leaving by a lot of energy. So you get the water at the bottom, and the water leave all the way up to the top of the wall. Guess what? Someone gave you that energy. It's the pump. The pump is giving work on you. The work is negative of the pump. It's being delivered to the pump. Make sense? So why the confusion? Why they didn't do this? Probably because the first people that worked on this or developed that system were really interested in the working in the Industrial Revolution, you know, when they first discovered the steam power and start making steam engine. And so you can see, like in a steam engine, what happens? We give him heat and we get work. And I guess they didn't want to keep saying, wow, look at that engine. The work is not minus 300 kilowatt. That's amazing. They wanted to say it's plus 300 kilowatt. Like we give him this mini heat in the cold and look at it. It's giving us plus or simply just like 400 kilowatt. So that was very convenient that a regular engine, steam engine will take heat and get warm. Right? Very good. So this work sitting over here is simply mechanical work, electrical work that you can see with your eye, you can use it, right? But there's another work that is actually happening and you are not noticing it at all, but it's happening in front of you. And when it comes to the first law of thermodynamics, that will cause a lot of problem if you don't count for it. And the example I would like to give to understand that work is, imagine if we are doing control volume on the student in this classroom. We are trying to figure out how much energy is here so that we can figure if the temperature is rising or lowering. Should we add more duct, HVAC duct to cool or not? And to calculate the energy in this thing, we are putting a control volume around and we are counting everything coming in. So a student come in and is very energetic, that doing a lot of work. A student that's come beaten up from work, he will come with very small energy, right? And that would be the internal energy of the student. And then there is a fan coming in and streaming stuff that will give us work inside, right? But then imagine there is a police officer, security officer sitting outside the door, and every student every student coming in the class, he shove you in the classroom. Okay, you are not just coming in the classroom, he kick you in. This actually brings a lot of energy with you, right? I mean, you come with all that kinetic energy. Of course, it dissipates when you roll on the staircase, that energy you release into temperature. But that officer is basically giving every student coming in energy. And when you guys try to leave from the on the other side, I actually recommend leaving from here and coming from here, so that, especially between two classes. But anyway, every time you're leaving, there's another police officer and he's doing the opposite. Rather than pulling you out, no, he's pushing you in the face to prevent you from leaving. And so in order to actually leave, the students in the classroom need to keep pushing on you so that you can, he keep kicking you in the face. And so everyone behind you, come on, man, get out. And they're pushing you. So then we have to exert more to actually let you go out. So it takes energy for you to leave. That work by the officer at the inlet and the officer at the outlet is actually happening in front of your eye, you just don't see it. And that is the work that you have to do against the pressure force. Those Newton sitting here, and P1 is in our way and P2 is against us so that we can leave. That pressure force per unit mass flux leaving, if you want to calculate that, it will turn out to be PV, or simply V over rho. And the unit is joule per kilogram. So the energy, I mean, it's kind of work in and out. Huh? But rather than putting it over here, they said, let's not put it here because let's keep this data for real work, things that we can really see. This one, let's just add it here, B2 over rho 2, and let's add it over here, B2 over rho 1. And so the first law of thermodynamics then now reads, now we read that Q dot minus W dot equal to M dot. And rather than simply U2, it's U2 plus B2 over V2. Plus V2 squared over 2 plus GZ2 minus, what's wrong? Minus M dot 1 multiplied by U1 plus P1 V1 plus V1 squared over 2 plus GZ1. And what is that small v that I'm writing here? Is it velocity? Is that velocity? Well, What do you think it is? This V, that PV, what is it? Specific volume, correct. Makes it its specific volume. So what is U plus PV? This is called U plus PV is called, anyone? I can't hear. That's the first problem in our homework, this guy. We are going to calculate this guy. What is it? U plus PV is enthalpy. This is H1 and this is H2. The enthalpy is U plus PV. So this is weird then. So when the flow come in, you would think he only comes with internal energy, but he also comes with PV. Sorry, when he leave with PV, P2, V2. And when he come in, does not only come with U1, he comes with U1 plus P1, V1. So he comes with H1. So the flux over flow coming in, the energy flux, unlike the flow in a box, if you tell me, well, not the flow box, but the energy in a box, if you tell me what's the energy over here, in that box, I would say internal energy, U plus kinetic energy plus potential energy. But if it's a pipe or an engine and flux is coming in, it's not just the U, it's the enthalpy. Okay, and it's coming from that work done by the pressure force. Okay, so the first law would actually read H plus V1 squared over 2 plus GZ. Right? This is for a system, you will have delta U. Okay, but for a control volume, he's explaining to us here what is that pressure force and what is the work done by the pressure force and how it turned out to be P over rho, which is simply PV. And so because of this, the first law would be Q minus W equal delta H plus delta kinetic energy plus delta potential energy. All right, so we can didn't we don't guess not. Okay, so maybe I should just start to keep cleaner for you. So simply will be Q dot minus W dot equal to M dot 2 H2 plus V2 squared over 2 plus GZ2 minus M dot 1 H1 plus V1 squared over 2 plus GZ1. Okay, and usually when it's steady state, M dot 2 equal M dot 1. Okay, and what if it's not steady state? What if it's not steady state? What should happen? If it's not steady state, then it's like this: Q dot minus W dot is equal to partial T. The unsteadiness part, if there is a difference between what is coming and what's going, then that difference will be stored inside the control volume. The control volume is building up his energy and building up his mass. So for example, M dot 2 should be equal to M dot 1, but if M dot 2 minus M dot 1 is not the same, that is partial T of M control volume. Make sense? So this is the unsteady continuity equation. The steady continuity equation is M dot 2 equal M dot 1. Mass coming in need to be equal to mass leaving. Otherwise, imagine if the flux coming in is not the same as the leaving. Either the pressure will increase until we die from the pressure. It's like a super, it's like James Bond movie. They increase the pressure not to kill us. or they suck the air and they don't let anything in, so they put some vacuum, still the air will disappear. Yes, but if that will be, most scenario will be controlled by this equation. The unsteadiness, the net difference between m dot out and m dot 2 is partial T of the mass inside the control volume. So you use this when you're trying to say empty a tank or something. That's what you will do. And when it comes to the energy equation, same thing. If there's a difference between the flux, then this sorry. So Q dot minus W dot equal partial T, and by partial T, I mean the unsteady rate of the energy inside the control volume. The energy inside the control volume is U, not H. H only when you are crossing the boundary. But inside the engine, you have internal energy only. So U plus V squared over 2 plus GZ, that's inside the control volume, plus M dot out multiplied by H plus V squared over 2 plus GC out minus M dot N multiplied by H plus V squared over 2 plus GZM. That is our control volume energy equation. Fortunately for us, this get canceled for what? For steady state, right? And M dot out and M dot in is usually the same because it's steady state. So to start with, it has the same mass. And so you end up with Q dot plus M dot N H plus V squared over 2 plus GZ equal W dot plus M dot out H plus V squared over 2 plus GC out. And I memorize it like this when it's undergrad. I always say Q minus W equal M dot out, energy out minus M dot in, energy in. But when you put it in that way, it makes total sense. You are basically simply saying Q plus energy in, those are all the things that's plus coming in, equal to work plus energy out. All the thing that is plus in the way out. Okay? And so now when people do this, apply this for different components, things get a little bit more simplified. Like you can see even more stuff. For example, a steam turbine. You know, a steam turbine that we usually give it that sketch like this, and we say, well, the steam come at 1 and leave at 2 and give work to the generator. And on a TS diagram, it's plotted like this. Here's 1 and here's 2. Let go like this. So when I write the first law of thermodynamics for it, what will happen? The work is there, but the Q is 0. Why the Q dot is 0? Because the turbine is, I mean, you're hoping it's isotropic, but for sure it's adiabatic. What's adiabatic? What does adiabatic mean? No heat transfer, right? No heat transfer. And actually, when you go to an actual power plant, you will see that they put the turbine, they wrap it in thermal blankets so that they can keep it from losing heat. And you know how the pipes will come from the top. They just like make the blanket has like a hole for it so that the pipe come in. It's like so cute. It's like a small puppy, you know, with like wearing a coat and his neck is coming up. It's like the cutest thing ever when you see the blanket for the thermal blanket for the turbine. But the point is Q leaving this tank is almost zero. And the potential energy between the inlet and outlet is almost nothing. One, because it's the same elevation. Two, because it is steam, not liquid. Steam, vapor in general, density is very small. So the potential energy becomes very little. So this also get canceled when it comes to a turbine. Never cancel this for a hydraulic turbine, for example, when we are doing like hydraulic dam, like Keystone. When if the Keystone turbine, if you cancel the potential energy, what else you got? I mean, the whole thing that's driving it is the potential energy. But for a steam turbine, you cancel the GZ. And surprisingly, you cancel the change in kinetic energy. How is that possible? I see the steam is like coming at very high velocity and leaving at very high velocity. But the difference between the inlet and the outlet is nothing compared to this edge and that edge. Okay, so then what is left from the equation? For a steam turbine, Q dot, sorry, we said Q dot is zero. It will be W dot, okay, minus W dot is M dot H2 minus H1. Or simply, work turbine is going to be M dot H1 minus H2. And so people just used to write it like this. But know that, and I personally loved every time I have any one of this problem, I just love to start from here. It made me feel smarter. You know, when I say partial T and stuff, it's like, wow, look at this. Like though I don't think I've ever solved an unsteady problem as undergrad, maybe one problem or something. But it's just like you start from here and you cancel that term and you feel like you own that first law. You know exactly what's going on. And you cancel the kinetic energy and potential energy. So I really encourage you to do this. However, Beben will not take points off if you start simply from saying this, work turbine is M dot H1 minus H2. You are fine. You know that it's like was a big thing and you cancel until you come to it. Okay? But for some problems, like the first homework problem, you really need to start from the beginning because in that problem, he actually is describing a nozzle, a conversion diversion nozzle. And the point behind those conversion diversion nozzle is what you think. So a conversion nozzle will look something like this. So the flow come into a smaller area. And that's like you watering the hose, watering the yard with a hose, and you will reach that corner in the yard, and you don't want to go because the hose is like you cannot stretch it. What do? You push on it so that the area gets smaller, so that the velocity gets faster, so that it can go all the way to the end, right? Because you are thinking AV equal constant. So you are telling yourself, if I just shrink the area, the velocity will shoot up because it has to have the same pressure. Sorry, the same mass flow rate, same Q. This is, so that's annoying because Q is the volumetric flow rate in fluid, and Q is the heat transfer rate in heat transfer. Okay, so maybe we shouldn't really, maybe we should call it V dot. Like yes, which is even more annoying because a lot of people don't know what the hell is that symbol. But anyway, it's just like the meter cube per second. How about that? So that conversion nozzle speed up the stuff, right? But the maximum it can do is Mach 1. You cannot get more than the speed of sound by this configuration. And a lot of people try shrinking it and making all kind of area they could never manage to do until one guy called De Lavelle. He was European. I think he was from forgot he was from Germany or somewhere nearby. He basically did this. Right after he went to the smaller area, he also went up, and suddenly he can hit for the first time ever supersonic speed. So with this conversion diversion nozzle, you can go to Mach more than 1. You can go to Mach 2 and 3. And that's why all the rocket engine, if you look to all the rocket engine, you will see them having this nozzle. Because once you hit Mach 1 over here, you can even go higher and higher. Okay, so now when we are in the first problem, if we are asked to analyze something like this and say calculate the enthalpy at the exit, and we're going to apply the first law of thermodynamics because this problem is all about energy. Things are converting, things are changing from maybe high enthalpy over here to maybe high velocity over here. So when I write the first law, why did I write the first law? Why did I think about writing the first law? Because I see the problem is about energy conversion. So my brain go, I need to balance the energy. And like energy in, energy out, probably that will give me a clue about what is the velocity at the exit, or the enthalpy at the exit, or the relation between the velocity and the enthalpy at the exit. Because at the end of the day, they need to be equal to the same amount of energy. So when we do this, can we say, well, it's like a turbine, and let me neglect the enthalpy, sorry, let me neglect the kinetic energy and the potential energy? Can I do this? Can I use this equation? Or should I go back to the first law of thermodynamics and keep the kinetic energy? I should keep the kinetic energy because this nozzle is about huge change in kinetic energy. This nozzle is created so that the V at the exit is way bigger than the velocity at the end. And when you do V squared, that will become even bigger, right? So that's why it's nicer to know what is the general form and simplify it for different problem rather than memorizing or getting used to just write the short version. Okay, so let's read the homework problem. So no, not this one. Homework 1. Come on, give me homework 1. Homework 1. So again, the first problem is just like to make a PowerPoint slide, and you're gonna put it as part of your homework, the first page of your homework, right? You will turn all your homework into PDF, and you will upload it to the Dropbox, right? So remember a clear picture of your face, things that are fun that you do and make me remember you. Maybe you are big in fishing, or maybe you fix cars, or maybe you are I don't know, collecting skateboard or something, just something fun. Okay, I like engine, and I like feeding birds, and I like gardening. Those are from my own yard. So the second problem, here is the second problem, and here is the conversion diversion nozzle. By the way, the guy who invented this, De La Velle, he was a mechanical engineer that was fired by his boss before he invented this. His boss didn't think he's good enough, and he fired him, and he is responsible for creating the conversion diversion nozzle. He also became very rich when he invented a cream separator. Like you get the milk, and he invented this machine that can take the cream away from the milk. He made a lot of money out of that. And he eventually came to the US, in Chicago. I think there was like a world exhibit or something, and he came and he showed his conversion diversion nozzle. Of course, this was also hooked up to a turbine, and that steam was turning the turbine. And that turbine was rotating with speed that no one had ever achieved before, because it was being hit by a supersonic steam jet, right? So that turbine, that nozzle is adiabatic. Adiabatic means Q is 0, right? But doesn't mean isentropic yet, right? So isentropic is when not only it's adiabatic, but it's also what make adiabatic isentropic. It has to be adiabatic, and what's the second condition to be isentropic? Adiabatic and adiabatic and no, not steady state. Adiabatic and Adiabatic is mean no heat transfer. That's the first condition. We need something else beside no heat transfer, beside adiabatic, to be isentropic. Reversible. What does reversible mean? No losses, no irreversibility, no friction, no mixing, no temperature difference across. So reversible means that it can go, like you take the flow this way, you can bring it back the other way. It's exactly, you restore himself. Of course, reversible process does not exist in real life. Reversible process is idealization of things where friction is so small to the extent that you can neglect it. So nothing gets lost. Okay, so that's what reversible means. And then when it's reversible and adiabatic, that means it's isentropic. Okay, so adiabatic by itself means that we can cancel the Q in the first law of thermodynamics. Isentropic means not only we can cancel the Q, we can also assume S1 equal S2. Make sense? So it's adiabatic conversion of nozzle. Here is the pressure P1 megapascal. I'm going to multiply this to 10 to the power 6 when I'm saying what's given. And velocity is 50 meters per second. It expands to a pressure of 0.013 megapascal. So he dropped, the pressure go down so much. To increase the velocity to 600 meters per second. Determine the final temperature if the steam is superheated in the final state. And its quality if it is in the wet region. Okay, so he's saying calculate the temperature if it's superheated and its quality if it's in the wet region. Okay, so let's see how we can solve this. So I'm going to start by saying what is given to me, and I'm going to say P1 is, what did we say here? Was 0.6, 10 to the power 6 Pascal, and T1 was 200 degrees C. So, you know, I know that I'm going to use the degree C because the steam table is requiring the degree C, but just so that my brain does not kill me, I'm going to add this, right? But we know that we don't really need it, but it just like feel comfortable to me to do this. And B2 is 0.13, 10 to the power 6 Pascal, right? And V2, ouch. And V1 is 50. V1 is 50 meters per second. And V2 is 600 meters per second. That's what is given. Now, what is required? Sorry. I actually thought that it's the opposite. Fine. Just remove that check. So what is required is, he said, find the temperature T2 for superheated or X2 for saturated. Okay. That gives me 30%. I don't know about you, but I cannot solve a problem without drawing a sketch. I mean, even if the sketch is just like an arrow showing what's given and what's required, and it turned out that when they did a survey of the students, of engineering students compared to general engineering in university, it turned out that engineering students understand pictures and figures more than regular students. Okay, so we like people who are engineering oriented, we can understand figure and charts easily compared to other people. Okay, it makes sense to us. So when I plot this, you know, and say 1 and 2, and I say T2 here is required, and I could say that H1 is given. Is it? Kind of, right? Why H1 is kind of given? Yeah, because I have V1 and T1. That's all I need to get H1. And V1 is kind of, ouch. What did we do? And V1 is given, and over here, V2 is given. And T2 is required. That kind of like tell me what's going on. I feel that, and I can do this like that, and I could say Q dot is 0. So that sketch kind of tell me there's input, there's output, this process is adiabatic, and if I plot this on a TS diagram, that would be even more useful for me to understand. So since this is steam, it's probably here, you know, at 0.6 and 200 degrees C. Maybe you don't get it, but I mean, if you just go to the steam table and check the special temperature, where is it? It's probably going to be superheated. And if it's wrong, you just put it later in the wet region or saturated region. But let's assume it's here. And if he expands isentropically, we don't know whether it is isentropically or not. If he expands isentropically, he will end up, say, and this is 0.13. So this is 0.6, and this is 0.13. He will end up here. But he could end up expanding like this. And so he could be out or he could be in. And that's why he's saying that if you are outside, give me the temperature, tell me this is on the TS diagram. Then what is this temperature? And if you are inside, of course, if you are inside, what would be the temperature? I will just go T saturation. What is T saturation at 0.13 bar? That would be the temperature, right? But I mean, that's easy. You just want to get the X. What is the X? Are you 1 or 0 or 0.5 or 0.7? Where are you in that place? So how do I calculate the X? What I always say that problems need to be solved from the end, not from the beginning. Meaning that, you know, like a lot of time when you look at the solution in check.com or like any other textbook, it's written like this. Step 1, H1, I bet he will go with H1 solution. And we, sorry. And we would say, see, that's why they have this plexiglass to save you from me. They would say H1 is H1 of P1 and T1. Go to 0.6 megapascal and 200 degrees C and get yourself your H1, right? And then what? He will go to the, and you will read every line and you will understand every line. But that's not how your brain works or should work when you're solving this problem. When you wake up in the morning, you don't just say, step 1, go to the restroom. You know, the Lego movie, everything will be fine. You know, like when he was following the instruction. So I have 3 kids, so that's why I see a lot of my cartoon movie. So you don't go up from the bed in the morning and say, step 1, take a shower, then get dressed, then have breakfast, then get the key, then leave and go to the job interview. No, your work go the other way. You would say, today I have a job interview. Let me get dressed really well. Okay, I need to wear this suit. I need to take a shower. I need to smell really good today. So we don't start by saying H1, and that's what I meant by you don't learn by just reading the solution. You have to come up with it yourself. So how do I start from the end? He wants x2. That's what's required. How do I get x2? Where is the equation that will give me x2? Where is the beef? Where is it? How can I get this x2? And then work my way backward to, I need h1, so I can do the first one. So how do I get x2? What is the plan? That's how I want you to think about every single problem. Okay? Rather than struggling with the step, you need to figure out what is the plan. And you fill in the plan to get this plan done. So I am thinking, because my experience solving a lot of problems, I think x2 always show up when we do what? When we try to calculate the enthalpy inside the wet region or the entropy inside the wet region. If I know the S2 or the X2, that's my way to get X2. So for example, if I know H2, H2 is HF plus X2. H2 is HF plus X2 times HFG. Of course, at 2. Does this make sense? So how do I get HF and HFG? That is what is state 2. That's at 0.13 megapascal. 0.13 megapascal. Known from the table, known from the table. So getting H2 will help me to get X2. Okay, I need H2. I need the enthalpy at the exit of that nozzle. Where can people calculate the enthalpy of the flow? Is it from the equation of state B equal rho RT? No. Is it from the continuity equation? M dot equal M dot? Does this have H2 in it? No. Where does H2 exist? First law, energy balance. If I say energy in equal energy out, that has H in it. So this equation is probably my last equation. And the equation before that is H2 plus V2 square over 2 plus GZ2 equal, multiplied by M dot, equal M dot H1 plus V1 square over 2 plus GZ1. What happened to the Q dot? I thought that the first law had a Q dot in it. What happened? Adiabatic. And what happened to the work? I thought that the first law had Q dot minus W dot. Where is the work? Why did I didn't write it? Is there any work inside this nozzle? You see a fan propelling the flow in. You see a turbine sitting there. There is no mechanical work. Is there electric wire going in and heating or doing electric power dissipation or something? No, there is not. So there is no work on this one. So the first law on this thing is simply Q dot minus W dot, cancel, cancel. Unsteady term, partial T stuff inside the control volume, E control volume, cancel. Plus M dot out, energy out, minus M dot in, energy in. Those are the two guys that will survive. And that's why it will read this way. Okay, so then again, working it backward, So that's what we will, this hopefully will have only one unknown, because every equation can only support one unknown. Everything else should be given, or we have another way to calculate that. Okay, M dot, do I know M dot? I can't, right? What's M dot? Rho AV. I was not given the area. Do I really need to calculate M dot? Do I need to calculate M dot? Yeah, they cancel, so let's not worry about that. I was not given the Z2. I mean, he never said it's horizontal or vertical, really. But again, it's steam, not water, not liquid. And it's okay to assume this equals 0. So maybe in the assumption, to be like super engineering, like to be really accurate, we should start here by saying assumption, neglect. We should say the first thing, neglect delta potential energy. Delta potential energy means that the change in the potential energy. We usually always, in thermodynamics, we say neglect kinetic energy to delta kinetic energy. We used to do this, but in this particular problem, no, we can't. The whole problem is kinetic energy. We will keep it this time, right? Okay, so then H2 is required. H1, you tell yourself, do I know it? He didn't give it to me, but he gave me P1 and T1. Then that's okay, I'll be able to get H1. There's a steam table for that, right? V1 was given, V2 was given, perfect. So this equation is good to get me H2. So that would be the second step. And so I guess the first step is to start with P1 and T1 to get the H. So now we had the plan in our head. I mean, you can do it in pencil the plan to the side, something, or the back, just to figure it yourself what's going to happen. And then come the solution. And after you set this assumption, then you start now neatly write B1 and T1 steam table, you know, or X steam or whatever, get H1. And then you would say the first law of thermodynamics will read, and now you can write the smaller version because you did this simplification on the side. It will simply say H1 plus V1 squared over 2 equal H2 plus V2 squared over 2. Ouch. So the sad thing is that you see people writing this because they copied from some solution, but they have, when it comes to other problem where there is a heater, for example, they don't know because they just copied that formula. Although, you know, understanding where it's coming from and probably the solution where this come from, wrote this first, or even better, wrote this first and cancel the unsteady term. Okay, so that is the difference between a homework problem where someone really just find the formula in the book and between someone who is developing the model himself. And that's what we need to be able to do by the end of the year. We need to be able to develop the model of any system based on just fundamental equations, no matter how new the system is. Okay, I'll give you more example later on. But so now we know this guy, we know this guy, we know this guy. You basic, sorry, this is the only thing that's unknown. Get H2. So now H2 and B2 steam table, and you will be able to get T2. If it's superheated, if it's not superheated, if it's not outside the dome, then you should get H2. So actually the way you do this is this. Before here, get H2 and compare with H2 greater than Hg. If H2 greater than Hg, then you'll be able to do this. And if H2 is smaller than Hg, then we obviously are wet in the wet region. And therefore, H2 is HF plus X2 times HFG. Get X2. And then once you get X2 or T2, you put it in one big box like this. Ouch. You put it in a big box like this, and you are done with the answer. All right. So I hope I explained, you know, how you need to solve the problem backwards so that you can come up with a plan for the equation, for the solution. And this hopefully explained to you the structure that I want to see. I think the sketch, Pippin shouldn't take points off if you don't plot a sketch. But I think you should really make it a habit to always come up with a sketch. And also in the quizzes and the exam, you always need to go step by step. Don't write everywhere. I see that all the time. One part here, one part there. It doesn't work. Step line by line. Okay? So problem number 3 is he is asking you to repeat this problem, but using MATLAB. So this part, what he's doing, he's calculating H2. Obviously, H2 need to be calculated from what? From B1 and T1. You need to add one line here, right? That say H1 equal X steam, right? X steam, and you would call it from the H and P and T, right? And you give him the pressure and the temperature, P1 and T1. And then after that, you will get H2 rather than giving it a number like this. No, H2 will be H1 plus V1 time V1 over 2 minus V2 time V2 over 2. That is what? That is the first law of thermodynamics, right? Now, what is the problem with this? X steam require H to be in kilojoule. This equation will use V1 in meter. So this equation does not have the right unit. The joule per kilogram for meter square per second and the kilojoule per kilogram. So what should we do? Multiply this by 1,000 and multiply this by 1,000. So that this way you maintain H in kilojoule and your first law is still in. Make sense? That is, you may want to take a copy. So now the quiz, we're going to go a quiz every day, every time. And this quiz today is going to be super easy because all I want you to do next week, we'll have more time, but it will be more serious. So I just need your name. And right now you write, if you are in the class, which row you are in and which, from the right wall, well, how many students are sitting to your right? And you put this in a paper, scan it with your phone and send this image or PDF, if you have that software, it's called Cam Scanner, and upload it to the Dropbox before 8:15. All right. Say that again. So the quiz need to be uploaded to the assignments and draw assignment number 1, quiz number 1. And you have 6 minutes to do this. But it just, No, I don't want you. Is it because it's not in front of everyone? I think they took them out. So I just want you to count your row. Number 1 is in front, and how many students are sitting to your left? Sorry, to your right. Starting from this one. So student number 1, 2, 3. You are number 3.
Can you go back to the
quiz? And for people online, same thing, except that you can write your name and just say, I am on Zoom. I'm following on Zoom. You scan it and you upload it to the Dropbox. Okay, and maybe I should give you more time because it's not really fair. This is your first time. So so guys, it's just your name and where you are sitting. There's nothing serious about this, okay? And so I'm gonna come here and try to give you more time. So let's make it let me give you more minutes, make it 25, okay? Okay, let's edit, let's see it. When it's available, let me edit, give them more time. So it will be available to 8, let's make it available to, how about this, 30 minutes, 8:30. Okay, and then over here the due date is 29. All right. Okay, so you have until 8:29. So that's a lot of time to scan a file and upload to the Dropbox, and you get 10 points for it. Okay, quiz number 1, just say where you are sitting. You got it? Is that clear? Yes.
how many chairs on the wall or how many students?
That's an excellent question. How many It's say here, now students on the right. It's how many students? You want to make it per chair? Does this make more sense? Chairs more make sense, right? Okay, let's count how many chairs, guys. How many chairs to the right? Sorry. Yes, it makes more sense. So placement in the row, first chair is on the right, east side of the class. How about chair placement in the row? Your chair placement in the row. So count the chairs to your right. You made the quiz more relevant. Good job. What's your name? Corey. You are a good designer of quizzes. So for online people, I just said, you just send me an email saying I am following online. That's it. Sure. So by the way, in the homework, I say that in the syllabus, when you see what's the format of the homework, I said in the homework, you have to sign the pledge. What is the pledge? I want you at the cover page of the homework, you need to sign, I didn't copy the solution from anyone or from check.com, and you sign your name. Okay? So very important on the cover, otherwise people will not grade your homework. We will return back to you until you sign the pledge, please, and send it back to you. Okay? All right, we are done. If you uploaded your file, you can go. We are done.